Okay, Sarah, or Becky, let's go live. I think it's ticking up, but very slowly now. Good, thank you. So, good afternoon and welcome to the Geological Society's meeting on climate change in the geological record. I'm Mike Daly, President of the Society, and I'm delighted to welcome you to this timely meeting. Before handing over to our conference convener, Dan Lunt from Bristol University, I'd like to share a couple of thoughts about today's context. As we entered our recent pandemic in early 2020, momentum was building for the transition to a low carbon world. But as global economies stumbled, oil became cheap, and the timing and effectiveness of vaccines took center stage, some people argued that the interest in climate change would wane. However, as we learn to live with the virus, the net zero agenda has actually become stronger than ever and is accelerating, at least in Europe and the USA. That sense of momentum is epitomized to me by two recent events. Firstly, in the past month, the cost of excess carbon emitted from Europe's power stations and industries rose from 30 euros a tonne of CO2 to over 50, in part a product of the EU's green recovery strategy. And the growing view of our own national bank and others is that 100 euros a tonne is coming soon. This will inevitably accelerate the move to renewables, and with it, bring higher energy, heating, and mobility prices. Secondly, just last week, the International Energy Agency issued a detailed report documenting their best way for the global energy sector to achieve net zero emissions by 2050. They defined what they called a narrow but achievable pathway to a 1.5 degrees Celsius outcome, and detailed a total transformation of the global economy over the next 3 decades. Amongst many things, this includes the end of petrol-engined cars by 2035, or new ones at least. No further requirement for new exploration and large development projects of coal, oil, and gas. And interestingly, gas demand peaking and starting to decline within this decade. Solar power increases by 20 times and wind by 11 times by 2050. And arguably the most challenging point of all, at least surprising to me, a reduction of total energy consumption by 2050. This in spite of population growth and the global economy being forecast to be about 40% larger than today. The metrics of GDP and energy consumption have grown in proportion to each other for the last 200 years. The above changes, if enacted, imply a major decoupling of energy growth and energy demand. This reliance on efficiency will be new ground for us all. The IEA has drawn both criticism and plaudits for their work, as the implications for domestic and industrial use become apparent. Resource production becomes clearer, and mobility becomes increasingly understood. The work was commissioned as a guide for the upcoming COP26 meeting in Glasgow. Published 6 months before that meeting, it presents a huge challenge and opportunity to the world's leaders, and particularly the host nation. The escalating European carbon credit price and the first truly granular description of what global net zero actually means is a daunting but inspiring moment. The consequences in terms of resource cost and security, our environment, people migration and conflict are unknown and mostly very difficult to assess. But for sure, the choices and decisions made during the COP meeting will impact us all, be there action or inaction. The earth sciences and today's subject matter lie at the heart of this increasing activity. Our understanding of changing environments and their course is a crucial underpinning of all this. And to support this critical issue, the Geological Society has raised climate and environmental change to be one of its main science themes for the coming years. The Climate Change Working Group paper and this meeting are milestones from which to improve and share our understanding and inquiry into what is happening to us. And more importantly, what is likely to happen next and what we can and can't do about it. And so, to our meeting. I'd like to thank Dan and his co-conveners for pulling this together and attracting some great people. Not least our guest speaker, Maureen Raymo, our 2014 Wollaston medalist, who will address the theme of the conference. Thank you to all the participants for their time and efforts in this, and I trust this will be an energizing and insightful few days. Dan, over to you.
So thanks very much, Mike, and thanks to the Geological Society for hosting this online event. I'm Dan Lunt, Professor of Climate Science at the University of Bristol, and as Mike has highlighted, the transition to a green economy really does represent a challenge, but also a really exciting opportunity for the sciences and engineering. And geologists will no doubt be at the centre of this through, for example, the environmentally sensitive extraction of critical metals, safe disposal of nuclear waste, carbon capture and storage. And this is a theme that will be developed in Rachel James's talk tomorrow. However, it is important to remember that the main driver for this energy revolution is to avert dangerous climate change and harmful climate-related impacts in the most vulnerable societies and ecosystems of our planet. And again, this is a theme that will be developed tomorrow by Danny Schmidt in the context of past climate impacts in the geological record. So what is this symposium all about? Well, back in 2010, the GeolSoc produced a statement titled Climate Change, Evidence from the Geological Record, which was then updated in 2013 to account for the latest research. And then a couple of years ago, 2019, the GeolSoc and the UK Paleoclimate Society jointly convened a working group to produce a sort of single up-to-date statement. And this was published at the end of last year in the journal of the GeolSoc. And that was titled, What the Geological Record Tells Us About Our Present and Future Climate. And this statement and the paper were structured around 9 key questions about the relationship between geology and climate change. And these questions were, firstly, what does the geological record of climate look like? Why has climate changed in the past? Is our current warming unusual? What does the geological record indicate about global versus regional change? When Earth's temperature changed in the past, what were the impacts? How does the geological record inform our quantification of how sensitive the Earth is to emissions or concentrations of CO2? Are there past climate analogues for the future? How can the geological record be used to evaluate climate models? And then finally, what is the role of geology in dealing with the climate emergency for a sustainable future? So this symposium is structured around these same 9 questions, although in a slightly sort of random order due to multiple time zones. And it provides an opportunity to summarize our understanding in these key areas and to show all these key questions and to showcase some of the latest exciting research through invited talks from the leaders in the field. And in addition to that, the GeolSoc has a commitment to support early career scientists through, for example, its early career network. And as such, we'll also be hearing from 5 upcoming early career scientists. Finally, as many of you know, we had an open call for abstracts for talks at this event and had a really nice large number of submissions. And in the interests of sort of inclusivity, really, we've given everyone who submitted an abstract a chance to present their work and opinions in the form of a 1-minute flash presentation and also an open poster session tomorrow. And I really encourage all of you who are able to attend tomorrow to stay around for those posters and to discuss with the presenters. So just a couple of final words on the practicalities before we start. I'm sure this won't be necessary, but all participants and speakers are reminded that they're required to abide by the GeolSoc meeting and events code of conduct at all times. Apparently, anyone found to be violating the code of conduct will be permanently removed from the Zoom event. We have our very own Jackie Weaver at hand to do that, should it be necessary. another practical point, there should be a Q&A button at the bottom of your Zoom window. Hopefully you can see that. And in there, you can type in questions for the speakers and also vote. You know, if someone else put in a question that you'd really like to know the answer to as well, then you can sort of upvote that question. What we'll do is the conveners will read out some of the, in the time we have available, read out some of the questions for the speakers to answer after their talks. But then also after that, if there are any remaining questions unanswered, the speakers will be able to sort of type in answers during the next talk. Okay, so without further ado, I suggest that we get started. So the first of our invited speakers is Professor Paul Valdes from the University of Bristol. So Paul is he is the leading paleoclimate modeler in the UK, if not in the world. Although I am biased because he was my PhD supervisor. So, but he was, the evidence of this, he was awarded the coveted Milankovitch Medal by the European Geosciences Union in 2015. He's tackled questions ranging from, the earliest Phanerozoic through the warmth of the mid-Cretaceous to the depths of the cold of the last ice age, and even millions of years into the future as well. And today he's going to be talking to the question, why has climate changed in the past?
So let me share my screen, and hopefully now you can see. Eventually, it's going to be slow. Oh, here we are. Thanks, Dan, for those kind words. I think I definitely owe you a beer or two next time, if ever we are able to go to the pub together. So it's a huge pleasure, a huge privilege, huge honour to be talking today and to indeed be the first speaker in this really potentially fascinating meeting. I was given the title of talking about how climate change, or causes of climate change in the past. And I guess I wanted to put a subtext to it, or a sub-story to it, in terms of saying that what I'm going to present is a story of external forcings on the climate system, but then internal feedback processes, which help to understand and explain many of the changes that we see in the geological record. It's a tough ask to do this. I actually do a lecture course of 20 lectures on basically this sort of topic, and I'm being asked to sort of summarize in 20 minutes 20 lectures worth of material. So I'm going to really just do a small subset of really what I could talk about. But before we get on to sort of about the causes of climate change, I felt I needed to show at least one curve showing how has climate changed in the past. I think there are going to be other speakers who will spend a bit more time on this, so I'm not going to spend a long time explaining this graph, but this is an updated version of an iconic curve in paleoclimate showing how climate has changed, or our best estimate of how climate has changed over the last 65 million years. And you can see lots of interesting features. As I say, I could easily spend my 20 minutes talking about this curve by itself, but you can see the sort of features that I want to sort of highlight. Obviously, is the extreme warmth of the early Eocene, and that puts into context the projections for future climate change. That in the worst case scenario, we're getting certainly into the Eocene, if not necessarily the very, very hottest part of the Eocene. And then you can see that climate has cooled, lots of variability associated with that, lots of abrupt changes. The classic one is at the Eocene and Oligocene boundary, where we go from the hot house to the cool house worlds. Now, I note that I use the word abrupt change at that EO boundary. I do want to emphasize or remind people that abrupt change is an abrupt change from a geological perspective. It's not abrupt when it comes to the human perspective. So when we talk about the future, we're talking about the next century or two. When we look at an abrupt change at the Eocene and Oligocene, we're probably talking about many tens of thousands of years to make that transition from the hot house to the cool house conditions. So it is worth always remembering that when it comes to the geological record, the difference in timescales that we're thinking about. Now, I have seen people basically use diagram equivalent to this to say, hey, look, climate has changed in the past, therefore humans cannot change climate. And of course, that's a spurious argument in some senses, in that it's a bit akin to saying that humans have always died, therefore COVID can't kill you, or smoking can't kill you. The issue here is not to say that climate has changed, and we know that there are natural processes. The big issue is climate, is it possible that we could be changing climate? And so it's not good enough just to look at this curve and say, oh, look, climate has changed. We've got to understand why has it changed. We've got to understand how sensitive, what this tells us about the sensitivity of the climate system. Does the climate system change with just it requires a huge kick in order to change it, in which case, well, we might not be so worried. But if the climate, it turns out, is very sensitive to small changes, then that's something that makes it all too possible that humans can make a big change. So let's go and think about, why has climate changed? What are the causes of climate? And this is another sort of almost iconic, or an updated version of an iconic diagram originally done by Murray Mitchell many years ago, and it's recently been updated by Anna van der Heydt, who's going to be talking later today. And what this is trying to show you is it's trying to emphasize sort of, the top row is kind of the forcing mechanisms that we might think about, and the bottom row is the sort of variability, or the bottom part of the diagram is variability, showing you how climate has been varying in the past. And you can see that on the sort of right-hand side, I've put the meteorological records. Sort of when it comes to thinking about the changes on diurnal cycle or even annual cycle, I'd argue that we're very much in the province of weather. That's really, and basically the instrumental record can tell us a huge amount about the mechanisms that are associated and the interactions that are associated with that sort of time scale of phenomena. But of course, when you go to the left-hand part of this diagram, then that's when we get into the geological story. And you can see immediately that, one of the first spikes, or first set of spikes in terms of the variations, are the classic spikes that many of us know in terms of changes in orbital variability, the so-called precession, obliquity, and eccentricity cycles at 24 to 100,000 years. But then you go further back and you can have to think about other processes that are important. Solar variability, in fact, solar variability covers many different time scales. We have to obviously worry about impact events. We have to worry about volcanism. We have to worry about just simply the moving of the continents and how that might impact on climate. Now, those are the sort of processes, if you like, that we know from many studies of how important potentially they are from a climate perspective. But the next challenge, if you like, is to understand and quantify that variability. And we know that correlation does not equal causation. So what we want to do is we want to try and somehow look at the mechanisms and quantify the mechanisms and be able to say exactly what bits of this variability are really important and how does it all work. And to do that, we have to go to some form of modeling, and love them or loathe them, they are a very important part, I would argue now, of earth sciences, and in terms of understanding how the climate system has changed in the past. And the key thing about climate models are that these are models which are based on the fundamental physics of climate. These are not models which incorporate a sort of a belief system. A business model might be a belief system. You might believe that you're going to sell 100 or 1 million widgets, and that's going to make you £1 million or whatever. When it comes to climate models, we start, well, I suppose the philosophers among you will point out that I do have a belief system, and my belief system is that Newton's laws of motion, ideal gas law and what have you, have applied for the whole of the geological record. And so that's my starting point, if you like, in terms of when I talk about a climate model. And a climate model is just an encapsulation of our best knowledge of the physics of climate and how they've applied in the past. And the diagram in the middle, I'm not going to explain, I'm afraid, but I put it in there just to remind me to talk about greenhouse gases, things like carbon dioxide, methane, water vapor, N2O. And the reason why I put it in there is to remind you that there's nowhere in a climate model where you put in a sort of an equation that says more CO2 equals warmer climate. That's not the way that the climate models work. The climate models work by putting in knowledge of how CO2 or water vapor or methane impacts on the electromagnetic spectrum. Basically, you can see here that CO2 absorbs infrared radiation around about the 15 micron window. And so at every grid point in the model, you do that sort of calculation of looking at the electromagnetic absorption and re-emission of radiation by the different molecules that are in the atmosphere. So it's a very, very detailed calculation. Even though with the biggest computers, we can't solve those equations perfectly. And so we do have to make approximations. That does lead to the models having some uncertainty to them, but it does allow us also to say something really very quantitative about how the climate system, or why the climate system has changed in the past. So let's think about what are the changing processes that we might have to try and model. And I've already mentioned volcanism. We can include volcanism into the climate models. Often quite a little difficult to include because it's really quite hard to completely quantify how much volcanism has happened in some of particularly the lit periods and the like. Very hard to put a sort of clear idea of what's going on. And similarly, actually impact events, it's very hard to put sort of numbers on, but people have done that, and you can include that into climate models. Orbital variability, obviously very, very important, and that goes into climate models, fundamental in terms of quaternary climate change and understanding that, and I'll say a few words about that later in due course. And it's also important, obviously, in all time scales. Unfortunately, it's harder to calculate the orbit, precise orbit, when you go back, for instance, into the Cretaceous, but you can be guided, you can do sensitivity experiments to ask the question of saying how sensitive do we think the climate is to orbit in those sort of periods. There are other things a little bit more obscure, but for instance, the Earth's rotation rate has changed over the Phranozoic. In fact, if you were back in the Cambrian, then the length of the day is only about 20 hours or something like that. The Earth has been gradually slowing down during that time, and you should put that into a climate model. Don't often do that. We have done that, and in fact, it was a lot of work, in fact, to discover that it's not that important. Other things aren't included in the model, and so this is an example. Cosmic ray flux is an example which is not included currently in most climate models. And the reason for that is that the whole cosmic ray climate story is really quite elusive and it's very contentious at the moment. It's contentious in terms of, first of all, the forcing mechanism. The curve I'm showing you is from Chavis and Visa, and you can see there's a very strong periodicity. A more recent work by, for instance, Smith et al. In 2019, using the same data as Chavis, or same material as Chavis and Visa, concluded that there was no oscillation at all in the cosmic ray flux, and they did vary a little bit, but there was no sort of periodicity in there. So we don't know exactly about the forcing, and we don't exactly understand the mechanism. There are arguments to say that cosmic rays can have an impact on cloud cover, and that impacts on climate, but exactly how that operates still is in a lot of consideration. So at the moment, we don't really we don't really change cosmic ray flux very much in climate models. So those are things that we can change. I'm going to show you an example of of a slightly simpler problem, just because of limitation of time. And I'm going to focus in on 3 different forcings and looking at quantifying how important they are. The first one is the changes in the output from the sun. Go back very to the very earliest Earth, and there's some debate about exactly what is the solar constant. The tradition is, the standard model is that it was about 25% of the current. But there is some debate. But if you look at the Phranozoic, you can see that during the Phranozoic, there's very little debate, and we know that the solar constant changes by about 1% per 100 million years. So in any modelling of the Cretaceous and the Eocene, you have to include that in your calculations. You also have to think about paleogeographic change. This is some paleogeographic reconstructions from Chris Curtiz. And the key thing, I guess, here to note is that different reconstructions are relatively robust in terms of giving very similar sort of position of the continents, but there is differences when it comes to things like the mountain reconstructions or the bathymetry. So in an ideal world, you'd consider different options for the orographic heights and the bathymetry to try and fully encapsulate some of the uncertainties we have in reconstructions of the past. And then the final part of my story that I want to tell today is thinking about carbon dioxide itself. So carbon dioxide, for some people, if you're a geochemist, you see carbon dioxide as a feedback process rather than a forcing. And that there's a feedback in terms of saying that higher carbon dioxide concentration changes the climate, changes weathering, and therefore changes, and that feeds back on the CO2 concentration. But the purposes of today's talk, I'm just going to treat CO2 as a kind of forcing mechanism. The dots on these diagrams are showing you various estimates from various different sources of where the CO2 is, how much CO2 we have. As you can see, there's considerable amount of uncertainty there. The lines are different sort of fits through that data. And I'm particularly going to talk about the black curve, which is towards the lower variation. I'm not using extreme changes in CO2. I'm using relatively modest changes of CO2 through the Cretaceous and Cenozoic. So what happens if I take those three forcings and apply that to my climate model? And I get out a representation of well, all things climate. I'm just showing you two examples, namely how temperature and precipitation varies over these different time periods. These are pretty pictures, pretty animations. I could again talk about those forever. But what I want to actually show is a comparison to data. And it's important, I didn't say when I was describing climate models, that when the climate models are developed, they do not use geological data in their development. And so the geological data is a true independent test of the climate models. And what I'm showing you here is the cyan-colored, blue-colored, whatever you want, is the observational data of benthic temperatures, ocean temperatures. And the black line is the model prediction of the same quantity. Namely, it's the benthic temperature in the model. And on the whole, I would argue you don't get all of the variability, the short-term variability of climate, but that longer-term perspective, the model is doing a really very good job. So by giving it the solar changes and the paleogeographic changes and the CO2 changes, we can reproduce the curve reasonably pretty well. And so that gives us confidence that the model is behaving itself. Interestingly, I show on the same diagram the surface temperature. So remember the Zakos curve is based on benthic temperatures. The surface temperatures out of the model are very, or follow a very similar pattern, but they are a little bit more subdued. Normally, that Zakos curve that I showed you originally was assuming that the surface temperatures mirror exactly the benthic temperatures. And here it's actually, they mirror it, but about at a 2/3 amplitude of change. So that's quite important when it comes to thinking about the observed past changes in global mean temperature. But because the model is doing a reasonably good job at simulating the benthic temperatures, at simulating the climate system, we can then use the model to do something that we can't do in nature. And we can do what-if experiments. Modelers like doing what-if experiments. And so the what-if experiment I'm doing first of all is, let's take my model and instead of changing everything, I just change the paleogeography. And to cut a long story short, we get some change, but it's only about a couple of degrees. This is looking at surface temperature, not benthic temperatures. So paleogeographic change alone is gives me about a couple of degrees of change. Sharp change at the EO boundary, and as I note there, actually, that change, although I'm calling it a paleogeographic change, it is actually the ice sheets, and there's been work by Rob de Conter and also by Dan Lunt, which have argued that Antarctica and Greenland change or initiation of ice sheet growth is related to CO2 too. So there is a CO2 small component here. But then I can do another what-if experiment where I include the paleogeographic change, but I also include the solar change. And because the sun's output was weaker 120 million years ago, it was colder then. And actually you can see that the combination, the two really relatively well-known forcings of paleogeography and solar, end up actually being really very small change in climate over the last 120 million years. So that those two forcings don't do anything. But you've already seen the headline story, which is that then if I add in the observed changes in carbon dioxide, we get a change in climate which is much more comparable to the the observed climate record. So I'd argue that the observed climate cooling that we see from the Cretaceous and Eocene down to the Quaternary, really it's very hard to explain that without invoking a role of CO2, and a really quite substantial role of CO2 in that change. That's not to say that everything is CO2. This is an example of work by Alex Farnsworth. Cutting a long story short, because time is catching up with me, is that I can see that regional change is much more complex normally. Regional changes, as Alex worked looking at the Asian monsoon. And to cut a long story short, I can't completely explain this, but when you compare the geological record of the Asian monsoon against model simulations, what you find is that carbon dioxide actually has a relatively weak role in terms of understanding monsoon changes, and that actually the dominant role is really related to tectonic processes, and particularly the uplift of the Tibetan elevation and complexity of that sort of process. So at regional scale, we've got lots of things, processes going on, but at that larger scale, CO2 clearly is playing a significant role. Not the only role, but a very significant role. In the last couple of minutes that I've got, I'm going to just now move a different time scale of problem and think about quaternary change. And as I said in my introduction, quaternary change, we're very familiar with that. We know we have a lot of evidence now to support the idea that the changes that we see, the 100,000 year and 20 and 40,000 year oscillations that we see in the climate system are related to orbital variability. But there's loads of things that are difficult to fully understand. And I emphasize this as another story, and a very probably even more compelling story of the importance of feedback processes. Because what I'm showing you on the right hand, my lava lamp animation on the right hand side here, is that the changes in the Earth's orbit around the sun changes the amount of energy that we receive at the top of the atmosphere. And this plot is showing you how the changes in solar radiation as a function of latitude and time of the year. And the number on the right is showing you the global annual mean change. And the key thing, the key take-home message is at the global annual mean, the changes in incoming solar radiation are minute. They are measured in, as you can see, tenths or more less watts per square meter. That means we're talking about 1/100th of 1% of the incoming solar radiation. These are small changes at the global mean, but huge changes seasonally. So the fascination about the orbital variability is that somehow the changes in seasonal variability in forcing end up in terms of large changes in the annual global mean. And again, to cut a long story short, the story is very much one of feedback processes. If you do the modeling, if you do modeling where you just change the orbit, or you change the orbit and the greenhouse gases, greenhouse gases and ice sheets, you can see that actually the orbit makes very little impact. I'm choosing here Antarctica and Greenland. It makes very little impact in terms of temperature. It does have a small impact at the obliquity signal, 40,000 year signal. But when you include all forcings, it does. The model's doing a fairly good job. And you can see that there's a contribution directly from greenhouse gases. That's the blue curve, but also a very important role from the ice sheets. So the ice sheets are and probably are the dominant driver in some senses of the changes over the last glacial interglacial cycle, not the orbit. But of course, then you ask the question, well, why did the ice sheets change? And this is some modeling work by Lauren Grigor at Leeds University, where she showed that a lot of the changes in the ice sheet are driven by the orbit. So the mechanism of change for glacial cycles is that the orbit changes. That orbit changes the ice sheet. In particular, what happens during the deglaciation is that you have warm summers which melt the ice sheet, and then the resulting climate that results in feedback and with the ice albedo feedback playing a very important role in amplifying the response. There is also a contribution from the CO2. And of course, the same comment in terms of feedback applies to climate CO2 links. I'm almost on my last slide, Dan. And again, it's the same sort of story, and particularly here, this is observational data, which argues that actually, although if you look at the Antarctic records, CO2 and Antarctic temperatures are almost synchronous, and there's a hint maybe that even that's the temperature slightly leads to CO2. When you look at global means, it's the other way around, and that CO2 is definitely lagging behind the changes in temperature. So that amplifies the temperature lags CO2. So let's conclude. Very whistle-stop tour. There are so many more things I could talk about. But really, I guess the take-home message is that there are lots of forcings, lots of feedbacks in the system that we need to worry about. There is no single mechanism that explains the whole of the geological record. There's lots of things going on, but it is difficult to understand the full changes in amplitude of temperature through the Cretaceous Eocene to the modern without invoking the role of greenhouse gases. The other thing is that, you know, we are in an incredibly exciting position as geologists in terms of being able to have a unique opportunity to quantify both our understanding of the climate system and test the climate models. And in the examples I showed you, in none of the examples did the models overestimate changes. So the geological record implies that the climate sensitivity, unfortunately, is sufficiently large that we do have to worry about the impact of human activity. And with that, I'll finish. Thank you.
Okay, thank you very much, Paul. We'll have I'm sure there's a virtual round of applause going on, but we'll
stop my sharing.
We'll move on to the questions. So we've got a few questions in the chat. So what we'll do, I don't think we'll have time to answer all of them live, if you like, but any that we don't get round to, and if you are able to answer them in the chat afterwards, Paul, that would be good. That would be really helpful. Just to pick a couple of them. One of them, one from Brian Catt, sort of notes that the models that you're talking about consider the radiative effects, but he questions whether they include things like lapse rate and convection and latent heat of evaporation. Are those effects included in the models that you're?
Absolutely, very much. All of those effects are included. You know, they are difficult to do, and so that they're not with their representation is not without uncertainty, not without error. But we certainly do include all of those sort of processes within the modelling frameworks, sort of thing, and they are very important, and they're very important parts of the feedback story, which you know, if we had much more time, I could talk about.
Okay, thank you. Another question from Sandra Pachier, who says, is ice extent prescribed or calculated in the generation of climate models that you're using, and in, you know, compared with state-of-the-art climate models? Like, how?
Yeah, very, very good question. So in the past, ice sheets weren't explicitly modeled. They were normally prescribed. And the reason for that was there is such a mismatch of timescale between a climate model where you can often only run it for a few thousand years, and an ice sheet which takes many tens of thousands of years to grow and decay. So that in practice, that was the past. And so in the climate model I was talking about, in all cases, we prescribed it, and then we could go and do offline calculations to see how the ice changes. In the current set of models, increasingly the current set of models are including ice, growth and decay of ice directly within the modelling framework, so that they're not being prescribed, they're being predicted as part of the modelling framework.
Okay, thank you. So I think we'll have time for one more, maybe two more. Another one, Steve Moxon sort of talks about, where is it? Oh, that was a question. Sorry, I've got the wrong question. Sorry, Brian Catt says, sort of asked a question about cosmic rays, really, and wondering whether the controversy is in the, whether they exist at all, or whether it's the magnitude of their forcing, or whether it's, the climate response to them. What's the sort of controversy, or let's say uncertainty?
I think there are two aspects to that. One of the biggest controversies really is in terms of the magnitude of their effect. So that we do know, and I can see some of your questions, although they're moving around at the moment. So is that we do know that there are cosmic rays are incurring on the Earth, and that we know that they change. Some of the biggest controversies are in the longer term perspective. Some of the beryllium records are on the sort of more quaternary time scales, but on the longer time scales, there's a controversy about exactly how big a change they are. But then, as I say, the second thing is actually trying to quantify how much that changes climate. And we know that clouds, droplets can be seeded by these cosmic rays going through. But this is where the problem with clouds is that there are many other cloud condensation nuclei. And so at any one point in time, the question is the properties of clouds impacted significantly by the cosmic ray flux? And the problem with a lot of this story is that there's certainly a hint of it. I'm not in any sense denying that that's a possibility, but pretty much all of the numbers have controversies associated with them. So Svensmark has done some very interesting work, but if you look at different, for instance, reconstructions of cloud cover in the observational records, you'll come up with different numbers, for instance, and things like that. So it remains a controversy, and that's why I think climate modelers would love to include them in climate models, but we need to kind of understand quantifiably some of these mechanisms of how cosmic rays impact climate.
Great. Okay, thanks very much, Paul. There's a few more. There's a couple more questions that we didn't have time to get around to, so I'll let you answer those when you get. But thank you very much for that talk and your responses, Paul. So the next talk, so the first of our sort of early career talks, if you like, is from Aidan Starr, who's a PhD student at the University of Cardiff. He's interested in the relationship between ocean circulation, carbon cycling, and climate change. And today he's going to be presenting his work on Antarctic icebergs reorganizing ocean circulation during Pleistocene glacials. So go ahead, Aidan, when you're ready.
Thank you. I'll just share my screen. So if you can see that okay. Thank you for having me. I'm really excited to be here. It is a flash talk, so I'll get right on with it. I'm going to be presenting some of the work from my PhD so far, particularly looking at the interaction of Antarctic icebergs with ocean circulation during some of these Pleistocene glacial intervals that Paul introduced. So to give a brief overview, sort of roadmap of the study, essentially what we're doing is taking climate records that are archived in deep sea sediment cores. Within these sediment samples, we look for potential carriers of proxy records for climate. So in this case, we're looking at a benthic foraminiferous, so a calcium carbonate shell, and debris, rock and mineral fragments that are deposited by melting icebergs called ice-rafted debris. So from these proxy record carriers, we can produce these data sets, sort of time series of paleoclimate change, and then using various statistical approaches, analysis, time series analysis, we can start to look at the relationship between them. And then using things like numerical modeling, we can test potential hypotheses and hopefully come up with a proposed mechanism to explain some of the stuff we see. So in this study in particular, we're using a set of sediment cores from just off the south coast of South Africa. And these are Pleistocene age sediments in this record, spanning about 1.5 million years. So one of the proxy record carriers that I mentioned, one that I'm particularly interested in, is ice-rafted debris. So as I said, these are kind of lithic grains and minerals, and in a sense, in this case, kind of chunks of Antarctica that have been picked up by the ice sheet and kind of frozen into the ice sheet. And then when icebergs carve off of that ice sheet, they transport these kind of this IRD, these fragments out into the open ocean. When the iceberg melts, this material accumulates on the sea floor. So using this and other paleoclimate proxy records, we can get an idea of how things like iceberg presence changed over time. This graph is potentially quite a lot to take in a flash talk, but the key takeaway here is that during glacial periods, during ice ages, so highlighted by these gray shading areas, we have high IRD, so we have more icebergs making it to this kind of this quite northerly site in the Southern Ocean. And we have a more negative carbon isotope value in the calcium carbonate fossils that we measure. And this represents a change in the deep water mass, so a change in the deep oceanography. And a key thing that we notice here is that changes in this ice rafted debris accumulation seem to be very tightly coupled to changes in that deep ocean circulation. And we can sort of probe this relationship further and use some kind of statistical approaches to try and understand this relationship a little bit better. And what we find interestingly is that regardless of the approach we take, we find that changes in that ice rafted debris tend to precede changes in that deep water mass, that deep oceanography. So for some reason, iceberg presence is changing systematically before changes in deep ocean circulation, at least in this set of records. And this is an interesting observation, and we might start to ask why, or how might we connect these changes in icebergs and changes in ocean circulation. One approach to this is to use numerical modeling. So here we use a sort of idealized experiments with an iceberg trajectory model. So based on our understanding of the physics of iceberg trajectories, we can kind of simulate where the icebergs will end up under different climate forcings. So for example, here we a bunch of icebergs into this yellow seeding region, and then under different climate states, we can see where those icebergs end up and where they melt. And what we see is that under pre-industrial conditions, so in the purple here, we get trajectories that are quite similar to what we observed from satellites. However, if we change the forcing to something like the last glacial maximum, we get an equatorward shift in where these icebergs are melting. And in fact, in panel B, I show an estimate of where the meltwater actually ends up in terms of latitude. And kind of long story short here, we see that just by changing the climate conditions, so without changing the actual carving of icebergs, we can have a fairly substantial redistribution of freshwater in the Southern Ocean. So under glacial climate forcing, we get a much more equatorward melting. As I said, these are idealized experiments. They do match with the data we see from a geological record. And it is a lot of freshwater to be moving around in the Southern Ocean. So how do we tie this all together? How do we put forward this kind of proposed mechanism? Well, perhaps changes in that Southern Ocean freshwater distribution can somehow trigger or be related to changes in deep ocean circulation. And so coming back to what Paul was saying about these feedbacks in the kind of quaternary climate system, we see potentially a kind of a new feedback system identified whereby the Southern Ocean, the distribution of icebergs and all of the things that change that distribution from wind to sea surface temperature, this can trigger feedbacks which can ultimately change large-scale circulation and ultimately climate. So that was my flash talk. Thank you very much. Thanks to my co-authors, my funding support, and of course my supervisors. Thank you.
Okay, thanks very much, Aidan. That's wonderful. Perfect timing. So we've got 5 minutes now for questions for Aidan. So I can see that Gavin Foster has a question, and he says, "What do you force your iceberg model with? What's providing those ocean currents, and how is that constrained?"
Sure. Good question. So the iceberg model is forced with another model, which is a kind of coupled general circulation model. This is the Cosmos model at the Alfred Wenger Institute. So this is just the pre-industrial and last glacial maximum kind of equilibrium states from those models. Okay, thank you. And do you have a feeling for sort of how uncertain that is, if you like? So the Cosmos model has one representation of
ocean circulation, but different. If you used a different model, that could be different. Maybe the ocean circulation would be different, and therefore the iceberg trajectories would be different. Do you have a feeling for how large an uncertainty that is, and whether you can validate that in some way?
Yeah, that again is an excellent question, and one of the benefits of the iceberg model is it's incredibly fast to run. So it's not something that we've done, but it would be really interesting to run that with different model outputs. What we do see is kind of comparing the sea surface temperatures in that Cosmos model with something like a compilation of last glacial maximum proxy records. We see quite a good match with where the oceanic fronts are and the magnitude of cooling, which we presume is one of the major controls on that iceberg trajectory.
Yeah, thank you. So yeah, like something like the PMIP model ensemble has data freely available that could be used to provide you some different alternatives anyway for what that ocean circulation might be like. Great, thank you very much, Aidan. That's great. Oh, we have one more. If you can answer it quickly in 1 minute, you can have one more. You can have one more question. David Naff says, "Great talk and data set. Thank you. Did you look into what type of IRD accumulates at different times? Is the composition of IRD constant through time, or does it vary?"
Yeah, another great question. We identified the mineralogy as best we could without a kind of comprehensive provenance study. So we predominantly have quartz with some potassium feldspar. So we see that through time, we generally have a fairly consistent percentage of quartz, which indicates a kind of continental Antarctic origin for the material, as opposed to something like a kind of volcanic or kind of a change in the source of these icebergs.
Great, thank you, Aidan. Well, there are a few more questions that have just appeared up in the Q&A. So if you're able to answer those afterwards by typing in your answers, that'd be really helpful.
Sure, thank you,
Aidan, for a really nice talk. Okay, so we'll move on now to our next speaker, who is another of our invited speakers, Anna van der Heydt. So Anna is at Utrecht University in the Netherlands. She's one of the world leaders in using the geological record to constrain estimates of how much the climate warms given a certain increase in carbon dioxide, in other words, the climate sensitivity of the planet. She also works on the dynamics of complex systems. But today she'll be addressing the question, how does the geological record inform our quantification of climate sensitivity? So when you're ready, Anna.
Okay, thank you. Let me share my screen. Yes, okay. Well, thank you very much for having me here. It's a great pleasure to talk about this question, actually, because it has kept me and many other colleagues busy for quite a while, not only from the geological record, but also more from the conceptual or theoretical side. How should we define such a number like climate sensitivity? So I'll try to give you an overview, relatively short. Again, as Paul already said, I mean, this could be easily a talk of several talks of much longer time. So I'll try to summarize a bit. So what we tend to sort of conceptualize is the idea that we have some forcing to the climate, and for the present day climate in the IPCC report, there are certain definitions of CO2 pathways. So that's basically, evolution, ideas of how the evolution of CO2 could be in the future. And there are different scenarios, like the red line, really a business as usual scenario when CO2 emissions would just increase down to the most, decreasing CO2 concentration in the RCP 2.6 scenario. Now we can translate this CO2 increase into a radiative forcing. So that would be a climate forcing. Again, the black line in these curves is the observation, so the observed CO2 concentration, the observed radiative forcing in that sense. And then we can put that into climate models and get the response. What happens with the global mean temperature under these CO2, under these radiative forcings, basically. And in the lower graph, what you see is the black line is again the historical period. It is the modeled historical period, and the gray shading basically tells us the spread of the models that what they simulate. Now that they extend into the future up till year 2100, and again the shading around the curves due to a certain scenario gives us the model spread. So there is a considerable uncertainty. The colored numbers in the right-hand side of the plot, they give us the number of models that have done this specific simulation. So for the RCP 8.5 scenario, there are 39 models that have run that, and that gives us the red shaded area. We can, of course, also extend that into more than 2100. We have most of these scenarios stabilize at some point. But what we basically see from the climate models response, that many of these models keep warming even if CO2 concentration is stabilizing. So we are not yet 2100. We are definitely not yet in an equilibrium. Now this is the general setting. So let's talk a bit more into what climate sensitivity really is. It is defined as the equilibrium change in global mean surface temperature after a doubling of atmospheric CO2 concentration. Now that sounds very simple, and so we double CO2 concentration, that induces a certain radiative perturbation, goes into the climate system. Assuming there are no processes as feedbacks in the climate system, we would simply get a change in temperature due to this radiative forcing, and the proportionality constant is actually very well known. That's the so-called Planck response. Due to black body emission, we will get, with increasing CO2 concentration, we will get a certain warming. This is relatively little. It's 1 degree per CO2 doubling. But of course, we know, and Paul has mentioned that already, there are lots of feedbacks in the climate system. So any process that affects also the temperature can feed back or can produce another radiative forcing, like albedo changes when there is ice melting or ice growing, for example. That feeds back into the climate system and generates an extra temperature response to that. So what we do in climate sensitivity is we define the equilibrium climate sensitivity as the change in the eventual temperature by the original radiative forcing, which is only due to CO2. And that brings us directly to the question, how can we quantify this? Now, the global mean surface temperature is not something that we can easily measure. I mean, we need lots of observations, but this is a number that has been defined for 40 years or more, originally for climate models, but increasingly is being determined by all kinds of information we have. Now, climate models are the first one, but of course also observations. These are instrumental records, but also historical records. The top of the energy imbalance has been observed for quite a while. Currently, it is quite some uncertainty on that, but also that gives constraints. And of course, the paleoclimate record. If you put, and that has been done in the latest IPCC report, if you put all this information together, you find quite a variation, but it comes down to an equilibrium climate sensitivity of 1.5 to 4.5 degrees warming per doubling of CO2 concentration. And this is actually a range that has, in the very earliest climate models, has already been stated there. Although we have much more data, much better climate models, there's still this big range of uncertainty on the equilibrium climate sensitivity. Now, more recently, last year, actually, there has been an assessment of the climate sensitivity so far by the World Climate Research Program, where we have basically used 3 largely independent lines of evidence to understand and to measure or to constrain the climate sensitivity. The first one is our understanding of all the different feedback processes that are in there. And I'll come to that a bit later, what all these feedback processes are. The second line of evidence is the historical record, and the third line of evidence is the paleoclimate record, so over much longer timescales. And by putting together all these three lines of evidence in a sort of statistical way, weighing the likelihood of each of these observations that we have, we can sort of generate likelihoods of climate sensitivity for each of these lines of evidence. So what you see in the graphs on the right is on the x-axis is actually the equilibrium climate sensitivity estimate in degrees. And on the y-axis is, you can think of it as a likelihood, as a probability density function of that. And in the upper plot, it's the colored lines give simply the three different lines of evidence, and the black line, if we combine them together, we get the black distribution of climate sensitivity. In the graph below, it is separated a bit more into the different lines of evidence, and in particular, the paleoclimate record has been separated into colder than present and warmer than present periods. And we already see here that we get different estimates for the colder than present and the warmer than present periods in terms of the equilibrium climate sensitivity. When it comes down to again, to look into this black line, the resulting combined all evidence climate sensitivity, we find the range between, largely the range between the two gray lines in the lower plot. That's 2.6 to 3.9 degrees for a doubling of CO2. So compared to the latest IPCC report, this has been constrained a bit more, and in particular, the lower end. So where all three lines of evidence agree on is that an equilibrium climate sensitivity below 2 degrees is extremely unlikely. So that was mainly the reason why this lower end has been shifted upward quite a bit in there. So what I'm going to talk in the rest of my time here is basically what are the uncertainties in this, and why is it so extremely difficult? Why do we have such a wide range of numbers, and why is it so uncertain? Normally, we think of uncertainty in terms of measurement uncertainty, but that's not what I mean here. I mean, there are other uncertainty, more process uncertainty, or other kinds of things that I will go through and highlight a few of them. Now, the first thing we need to do is we need to talk about timescales. Paul has already mentioned that the idea of an abrupt change in our climate today is very different from what happened, for example, at the Eocene-Oligocene boundary. So we need to talk about timescales. We have slow and fast processes, and that do play a role in the equilibrium response we get. The second point is, and this is already I think the most important point we can learn from a geological record is that all these feedback processes are not constant in time. They do depend on where we start from. So is it a warm climate? Is it a cold climate? Does it have sea ice? Does it have no sea ice, for example? And the relative strength of these feedbacks will change. Third, I will go a bit into theoretical considerations, because actually when we measure or we determine climate sensitivity from the geological record, we do slightly different things than when we determine it in a model, and because we never really reach the equilibrium within the model. And finally, I'll discuss a bit about tipping points in the climate system and how they potentially could impact our estimates of climate sensitivity or transient climate response. So to the first point, when we think about what kind of processes affect the response in terms of temperature, then there are many different timescales available. We know that clouds and water vapor, lapse rate, they change relatively fast in the order of years, maybe even faster. And on the other end of the spectrum, we have very, very, very slow processes like plate tectonics, we have weathering processes. Also, the land ice sheets are really very slow processes eventually. However, what you also see is that these arrows indicating the timescales on which each process acts, some of them are very long. So we can have changes of vegetation, for example, within decades, but we can also have changes in millennia. what we do in the practical sense when estimating climate sensitivity, we usually draw a line at around 100 years and call everything that is faster than 100 years fast feedbacks, and everything else the slow feedbacks. And then we have to remember that we, well, all the complicated climate models, we can boil it basically down to saying that the time evolution of the global mean temperature depends on, well, changes in radiative forcing. And this can be due to something that we call an external forcing. That can be orbital forcing, for example, but it can also be CO2 in this case. It can be the slow processes. It can also be the fast processes. And it can be, well, it will be the change in temperature as well. That's the outgoing long wave radiation. So when we define our climate sensitivity, we then use the change in temperature divided by the change in radiative forcing, and that's the RCO2. That gives us what we call the Earth system sensitivity. And for that, if we want to measure that from the geological record, we just need records of temperature and CO2. I say just because the global mean temperature is already tricky to evaluate, but still we can have records. And if we have different points in time where we can measure or we can estimate the global mean surface temperature and the atmospheric CO2 concentration, we can get an estimate of the Earth system sensitivity. And in the graph, in the left graph below, you can see that, well, for various periods in time, you can estimate these temperatures. If you would like to estimate the Earth system sensitivity, you have to compare 2 points in this graph with each other. And the slope basically gives us an indication of the Earth system sensitivity. Or we compare everything to the pre-industrial, that's also possible. Now, what we want is the equilibrium sensitivity, and the equilibrium sensitivity is basically based on the fast feedbacks. That's why I showed on the previous slide this separation into fast and slow. So we need to correct for the change in slow processes, for the change in ice sheet cover, for example. And we can do that if we have records of all these slow processes. Now, ice cover can be reconstructed relatively well, but there are others like vegetation that are more difficult, but still you can get estimates of that. If you do that for all different slow feedbacks, you can end up with an estimate of the equilibrium climate sensitivity, and that's given here in the, well, for the same points in time on the right graph, where the points, the red points, well, they are corrected for some of the slow processes. And instead of giving the absolute global mean surface temperature, they now give the surface temperature change with respect to the pre-industrial. That's why we have the red point at 0. And there as well. And the bluish shaded area, that gives us the IPCC range of equilibrium climate sensitivity, this 1.5 to 4.5 degrees per CO2 doubling. And that shows that the geological record largely falls within this range, although there are some points suggesting higher values of that. That's what Paul also already mentioned. Now, the second thing I would like to discuss, and that's actually an interesting one that we really have learned from the paleo record, is that equilibrium climate sensitivity is very likely state dependent. And what do I mean with this? Now, suppose we take records of the last 800,000 years and we reconstruct the surface air temperature anomaly. That's in the graph on the y-axis. And we plot all these observational points or record points versus a radiative forcing anomaly. All the colored dots are basically points in time of this record. Then, if we would estimate equilibrium climate sensitivity from that, we would like to draw a line. And the slope of this line gives us the climate sensitivity. However, what you clearly see from this plot is that this is more a banana-shaped curve. It's clearly not a straight line. So if we take only the yellow points, the warmer climates, the interglacials basically, then we would draw the red line as a slope. And if we would only take the blue lines, so the deep glacials, basically, we would get a smaller slope in there. So that means that in glacial climates, the climate sensitivity is very likely smaller than it is today in an interglacial climate. We can extend this idea a bit more to all kinds of other times in the past. Now, this graph contains partly the same data, but it is drawn a little bit different. On the x-axis, we have the temperature change with respect to pre-industrial, and on the y-axis, we have the corrected for slow feedbacks system sensitive equilibrium climate sensitivity. So, on the left, you have a couple of points that most of them come from the Pliocene, Pleistocene period. And you very often see this variation in the lower sensitivity in the cold climates than in the warm or present day like climates. And on the right, there are a couple of other periods added. Many of them come from actual climate models. The squares actually come from climate modeling, while the dots, the circles, come from observations. But what we see here also is there is not a very clear relation to temperature, but there is a variation in climate sensitivity depending on the on how warm the climate is, basically. In this World Climate Research Program assessment, all these data points basically have been put together into the likelihood of the cold and the warm climate. And what we see here again is that indeed in the cold climate, it seems that it's more likely that the climate sensitivity is a little bit lower. There are suggestions why that is. It probably depends on different feedbacks being active in the very cold climates, which have a lot of ice and different vegetation. So there are feedback processes responsible for that. And we understand that. Now, the third thing I would like to discuss briefly is think of the climate system as a combination of possible temperatures and radiative forcings, basically. And when we are in the glacial, interglacial cycles, we can say that, well, we move around on this gray shaded area. We have somewhere fast transitions from the colder to the warmer ones, also back more or less fast. But the climate system simply moves around in this area. And when we measure, when we have time series records, we measure 2 points maybe in this warm area. The slope gives us the climate sensitivity. We can do that also from another point in time, and that is maybe in a cold, comparing to cold glacials, that gives us another slope. Now that is the strategy to determine climate sensitivity from a geological record. What we are doing now, and also what we mostly do with models, is actually something different. We start from one point and then we add radiative forcing, but the system is not in equilibrium with that. So it moves out of the gray shaded area of the possibilities, and then it will move back eventually in some way to another equilibrium after many hundreds of years, maybe even longer. And we really don't know from the geological record this pathway to that equilibrium. Now, finally, I come to the last point very briefly. I know I'm over time already. There have been a number of climate tipping elements being suggested, and most of them involve abrupt change. And again, abrupt depends on the system itself. I mean, ice sheets may be abruptly changing, but still take a while longer than what we would call abrupt, for example. While sea ice is clearly a very quick change possible. Most of these tipping elements show rather regional impact. And they have been more or less well studied. So some of them will induce sea level rise, extra warming, or whatever kinds of monsoon changes. All these are more regional changes, and it's not so easy to assess whether there will be a huge impact on the global mean temperature directly, at least. But what we really don't know is how these tipping elements are coupled. And so suppose the Greenland ice sheet would melt, it will deliver a lot of fresh water in the Atlantic Ocean. So the Atlantic Ocean circulation could collapse, and that would shift precipitation patterns such that maybe the Amazon rainforest can die off. Now, this is a thought experiment. It could also be the opposite way. It could be stabilizing in that. But what we really miss here is the knowledge about these interactions between different tipping elements, because eventually, if there is a cascade of these tipping elements, it could feed back on the CO2 concentration. So if the rainforest dies, for example, we would add an additional CO2 concentration. So in that case, we would move back to equilibrium, not like the orange arrow, but maybe we would move more to the right side in the radiative forcing, because we can extra carbon cycle feedbacks. Or we could have the opposite way and move somewhere else in there. So that adds another uncertainty to where we really would end up eventually, even if we know the equilibrium climate sensitivity. Now, to summarize, I've discussed these different points, and I hope I've given you some insight into how we can learn from the geological record on the climate sensitivity, the climate response. Thank you.
Great, thanks very much, Anna, for a very nice talk. Right, we've got some good questions coming in, so I'll put some of those to you, and then if you could answer some of the others by typing in the answer afterwards, that'd be great. Thank you. So there's a couple of questions from Ashley Francis, who's sort of talking about the recent historical record in comparison with what you get from the paleoclimate, and the fact that some of the estimates based on the historical record are a bit lower than what we get from the paleo. I wondered whether you could discuss that a little bit and maybe talk a bit about the pattern effect and the reasons why that historical climate sensitivity inferred from the historical record is lower than what you get from the paleo or from a model, or like the true value, if you like, of climate sensitivity.
Yeah, well, thank you for that's a very good question. I mean, indeed, you would think that the historical records might be more accurate in a sense, because the paleoclimate record is well, that's very often indirect proxies. On the other hand, the paleoclimate record very often gives us the much more extreme situations than the historical record, and therefore we in a sense we have a higher signal to noise ratio. So you could argue that it's equally valid. Now, about the lower estimate from the historical record, again, this depends in a sense on the different feedbacks at work here, and the pattern effect is also in a sense related to past feedbacks changing over time, and that's very likely that happened in the historical record, that we didn't have exactly the same strength of very fast feedbacks in here, like sea ice and cloud feedbacks and so forth, that could potentially give us a lower estimate of the climate sensitivity from the historical record.
Yes.
Very brief, sorry.
Yes, thank you. Sorry, I was muted. I meant to say thank you. Sorry. Yeah, so there's a lot of recent work about the pattern effect showing that that we understand why the historical record shows this low climate sensitivity, because basically we were in a transient state, not in a full equilibrated state, which is what the definition of climate sensitivity is. And as the patterns of SST change in the Pacific, the feedbacks change exactly like you said. So then there's another question from Michael White, who, right at the beginning of your talk, you sort of talked about business as usual. And he questions whether this is really what we should expect now, given that different climate policies are coming in, and is it really fair to consider business as usual when no one knows, but it may be a sort of an extreme scenario?
Yeah, I think this has evolved over time. I mean, these scenarios have been developed for the latest IPCC report. This was in 2013, and there I think they were considered as sort of business as usual. But of course, in the meantime, this RCP 8.5 scenario really has evolved into a quite extreme scenario. that's perfectly correct.
Yeah, thank you. And then we have another question. I can't remember who asked it, but one question about saying, should we really have this focus on equilibrium climate sensitivity, the Charney sensitivity, if you like, with only the short-term feedbacks, when in fact, you know, some of these longer-term feedbacks, it's not like they suddenly appear in 1,000 years' time. They will be, you know, they will be playing out themselves now. Like, do we have too much of a focus on Charney sensitivity, and should we really be considering system sensitivity or some combination of the two?
Well, the Charney sensitivity is clearly a very good measure also to compare the response of observations and different climate models. So it is a very good measure, but it is in a sense not very practical. So I think what we should do is we should focus on the equilibrium climate sensitivity, but also on all kinds of regional effects. And I would call it the general climate response, because that is of much more practical value if we know how whatever variability changes, regional monsoon changes, maybe variations in the equator to pole gradient, maybe some more global measures, but more regional measures, extreme events, for example. So we should definitely come up with a better concept. Well, not better. I think we should come up with additional concepts to measure the more practical effect of the climate response than just looking at equilibrium climate sensitivity. But it remains a very important measure to compare things with each other.
Great, thank you very much. I know let's see if I can find a quick question that you could maybe answer in one minute. Gavin Foster says, you know, with all these nice talk, with all these complexities, where should geologists focus their efforts to better understand this, you know, the state dependence of ECS and tipping elements? What can geologists do to help answer those questions?
I think in the geological record, there's probably, there should be lots of evidence for tipping points, tipping elements. And there are some, like these Dunskat-Oeschke events, but there's probably more in the earlier record, which are maybe on longer timescales. But I think we can learn really a lot on these tipping elements from the geological record.
Great, thank you very much, Anna. You did manage to. It was a very big question, but you did manage to answer it in less than a minute. So well done. So thank you very much. Thanks very much, Anna, for your talks and for your talk and for responding to those questions. There are some more questions in the chat, so if you have time to answer those, that would be fantastic. Thank you. So we will move on to our next speaker. So our next speaker is another one of our early career speakers, and we have Rebecca Orrison here with us, all the way from the University of Albany in the US, where she's a PhD student. So thank you for getting up early and being here since the beginning of the conference. So thank you. She's interested in the variability of the global climate system, the sensitivity of the system to internal and external forcings. And today she's going to be presenting her work on the mechanisms of South American monsoon system response to external variability over the last millennium. So thank you, Rebecca.
Thank you very much. And thanks, Anna. That was a great motivation for some of the research I'll be presenting today. So I'm looking forward to sharing with everyone. All right, so this work is from the first chapter of my doctoral thesis, which is currently being prepared in a manuscript. And today I'll be talking about the mechanisms driving South American monsoon response to external variability over the last millennium. So this is a shorter perspective, looking at a shorter part of the geologic record. So to motivate the work today, I'll just explain a little bit about what the South American monsoon system is. It's the leading mode of rainfall variability and source of rainfall in South America, and really important for agriculture, drinking water, and also hydropower. So understanding the monsoon is important for understanding the future of energy generation in South America. Some of the key dynamical features of the system are the equatorial trade winds that converge into the intertropical convergence zone. And this brings moisture into the system and into the South American low-level jet, which is deflected off the Andes and channels south, bringing moisture into the convergence zone. Here, the SACZ, the subtropical Atlantic convergence zone. And this convective system is fueled by this incoming moisture and triggered by subtropical baroclinicity. And then the key mechanism I'll be talking about this afternoon is the Bolivian high Chacal low system, which develops as a result of latent heat released from strong convection over the Amazon. So the current state of the Amazon rainforest is really an important trigger for this development of this system, and it triggers a Rossby wave response across upper levels of the atmosphere. I explore the South American monsoon system through a proxy analysis using speleothems from cave records, ice cores, and lake sediments. We can find stable oxygen isotopes, which are archived. And these are really good recorders of the water cycle or the hydrologic variability. They don't record just precipitation, but are kind of an integrated record of the hydrologic variability across the domain. So we know from previous research that these isotopes are, here we're in the figure on the right, I'm showing the correlation between the spatial footprint of precipitation and the isotopes recorded from a climate model. And there's a really good correlation. So we're seeing that these isotopes can really represent the system as a whole. However, this analysis is often linking, or has often been performed by interpreting individual proxy records, and so sort of an intercomparison of records. In my work, I present a network analysis, which I think is a way that we can better understand the influence of the forces that are influencing the variability of the whole region and how the system is varying coherently across the region, and it's able to pull that signal from the noise or the kind of local conditions that influence changes in the isotopic variability recorded in these archives. So this network decomposition, looking at a network of proxy records, is really not only able to show us how the system changed, but it can break down the variability into distinct modes, which can then be linked to specific mechanisms of why the climate has changed in the past. And so in my work, I explore decomposition using 14 different proxy records, which have subdecadal resolution, and I'm extracting the leading modes of variability. So the majority are speleothem records from cave sediments, as well as an ice core and a lake core sediment. And so this is kind of geologically grounded, but in the more recent record, as I mentioned. And so I'll just present, this is the kind of these three leading modes of my work. And I'll just highlight the first mode today and talk about the spatial and the temporal characteristics of this mode that I'm finding. And so to draw your attention to the rightmost figure, this temporal variability, or the principal component time series of the first mode of this decomposition, we're seeing that in the early part of the record, there's more positive values or more enrichment of the isotopic record. And then in the later part of the record, sort of this blue shaded period, there's more depleted or more negative values. And so these are really corresponding to the historic record of global temperature change that we understand, where in the earlier part of the record, this pink highlighted period was the medieval warm period or the medieval climate anomaly. And so we're seeing that in the later part of the record, it corresponds to the Little Ice Age or a kind of cooler period in the global average temperature. So it's really interesting that we can pull this, this same feature of global temperature change out of the leading mode of variability from the monsoon. To turn now to the spatial mode, in the first mode of variability, on the rightmost, on the left figure, this is the EOF, the first spatial mode of the decomposition, and on the right, overlaid is the upper level or kind of upper tropospheric wind fields that show this Rossby wave response, as I discussed in response to the tropical heating. And so this is a really, this suggests that the second mode is modulated by this tropical latent heat response in response to tropical convection. So through this decomposition of our proxy modes, we've seen that the climate has always changed and it always will. But in order to have a closer look at the reasons why the climate has changed, it helps to explore through something like a proxy network where we can really extract these individual modes of change. And so we've seen that we know that the temporal variability can be linked to external forcings that are known over time. For example, the interhemispheric temperature gradient during the medieval climate anomaly or medieval warm period and Little Ice Age. And the spatial variability is linked to the known patterns that we can link to known mechanistic processes within the system, such as circulation changes driven by latent heat release from convective activity. And so the implications of this is that by understanding the mechanisms associated with climate change, we can also gain some insights into future variability of change. Thanks.
Great, thank you very much, Rebecca. That's fantastic. So we've got a bit of time for some questions. I can't see any in the chat at the moment, but maybe while people are typing in, I'll ask you a question. At the end there, you talk, it's really nice that this this method, this decomposition, if you like, can be used to look at mechanisms. And I guess the mechanisms you came up with were sort of they were, in some ways, you could think of them as actually responses of the climate system. You said one of the mechanisms was interhemispheric temperature gradient, another one was convection, but convective changes. But I guess the question then becomes, what causes them to change? What ultimately was the forcing that caused that interhemispheric temperature gradient, for example, or what causes that change in convective ability?
Right, so that's a fantastic question. Yeah, so we know that the medieval climate anomaly and the Little Ice Age were in response to external forcings and changes in volcanic variability and solar variability over the last millennium. And this mechanistic change, the changes in the Bolivian high, this is really linked to that latent heat release through tropical convection. And so as we're seeing the changes in that time series related to the interhemispheric temperature gradient and linking this mechanism to that time series, we can see that there's going to be a response of the latent heat, a response of the monsoon system to the change in that interhemispheric temperature gradient. And so this kind of weakening or enhancement of the monsoon, you might say, as a response to that change in temperature. So an enhancement of the Bolivian high in response to an increase in latent heat driven by an increase in convective activity over the Amazon, and then a decrease in the magnitude of that latent heat release driving the Rossby wave response. And so kind of linking to the talk of our previous speaker, if there are changes in the footprint or the spatial distribution of the Amazon rainforest and changes in the convection associated with the monsoon, we could expect to see changes also in these internal variability, in internal dynamic processes.
Okay, thank you. I think we've probably got time just for one really quick question. This is from Leon Clark. They say, it looks like there is some periodicity in your speleothem Delta 18O record and the top panel in your figure. Do you have any idea about the duration of these cycles or their origin?
Yeah, I think this is referring to the first principal component time series. And so there is some low frequency variability, but this is what we link to the interhemispheric temperature gradient and these changes associated with these two distinct climate periods.
Okay. Do you know what was the period of those the oscillations? Maybe it's what you can type in.
Multi-centennial changes in the system. Yeah.
Okay. Great. Well, thank you very much, Rebecca. There's a couple of I think there's a couple of other questions there. So if you have time during the next speaker, it'd be great if you could respond to those or during the break. So thank you very much. So we'll move on to our last speaker of this session before the break. And it's a real pleasure to have here Darrell Kaufman. So Darrell is the Regents Professor at the Northern Arizona University. So he's someone else who's got up early this morning to attend. So thank you very much for that. He's on the scientific steering committee of PAGES, the Past Global Changes organization, and in his role as lead author on the forthcoming 6th assessment report of the Intergovernmental Panel on Climate Change, the IPCC, he's really been, I think, the main person spearheading efforts to extract as much sort of policy relevant science as possible from the geological record. So I think, we all have a lot to thank him for that. So it's a real pleasure to have him here. And today he's going to address the question, is our current warming or current climate change unusual?
Great. Thanks so much, Dan. Let me go ahead and share my screen here. And goodness. I'm sorry, I need just a moment here to get my...
That's fine, no worries, take your time.
Yeah, thanks. I was hoping to find my, here we are.
Great, I can see that.
All right, that's good news. So thank you so much for inviting me and for that introduction, Dan. I wanted to commend the Society's working group on climate change for that scientific statement. I think it's really useful for communicating with a broader audience, as we're seeing here today. And I think those questions really help to gauge our scientific progress within the community and help us to focus some of our research priorities. And I've been asked to reflect a bit on the question, is our current warming unusual? So I'm really happy about this question. I really like it very much. I think it's appealing in a number of regards. It's a question we often hear. It's popular. It provides sort of the context for the ongoing global warming. People sense that the world is warming, and I think they quickly realize that the instrumental records are really insufficient in order to provide the perspective we need to really understand just how unusual it is, climate change. So in some ways, this question serves as an intuitive detection and attribution. I mean, if the current warming looks unusual, if it's weird, then it's probably not natural. The question is also extremely policy relevant. We're talking about climate, about temperature specifically, about global surface temperature. And that is the metric that the Framework Convention on Climate Change chose to essentially monitor the extent of global warming. It's indicative of the surface energy imbalance of the planet. It responds quickly to forcing, unlike some of the cryospheric or long-term changes in the carbon cycle. And I think I could argue that it is among the most well-known climate variables over multiple timescales. The question is also scientifically significant. The word unusualness is a bit squishy, but I think it's essential that to answer the question that we really need well quantified reconstructions of past climate states at a global scale. We need those to evaluate models that Paul talked about earlier, to constrain the equilibrium climate sensitivity that Anna discussed, and some of the other questions that came up in the Society's scientific statement. It's also, the question is very timely. It's just in the last 5 years or so where we have new resources. We've had an explosion of new records of past climate variability. We have new proxy types coming online. They're better dated. We're harnessing the power of those data by developing large compilations of proxy records of the type that Rebecca just talked about for South America. There's new software coming online, new proxy system models that enable us to better use the information within our proxy climate data sets. All right, so in order to address this question about is our current warming unusual, I want to focus on essentially 4 ways in which I think that the evidence shows that it is unusual. And I'll discuss each of these in turn using examples from superficial archives of paleoclimate information, all of which have been published. So the 4 ways that the current warming is unusual is it's been a long time since it's been this warm. The warming has reversed a long-term cooling trend, and it's warming rapidly, and it's warming almost everywhere. Okay, so the last IPCC report, AR5, was published in 2013, and the authors did a really careful job of reviewing all of the major studies of temperature variability, especially over the common era, the last 2,000 years. And this is a summary diagram that plots the time series for 12 of the prominent studies that they reviewed. So each color is a different study. For the rest of my talk, I will be showing graphs like this, where time is organized from left to right, moving forward. And in every case on the y-axis, I'll show temperature. It will be an anomaly or a change relative to some reference period. In this case, the authors chose the century that ended in 1980. So most of these data are based on tree ring evidence with it's very evolved science that is able to extract annual scale resolution of temperature and other climate variables. So most of the studies are tree rings, but there are a few that were included in blue here that also include evidence from sea surface temperatures as well. But in the end, the IPCC during the last assessment report essentially resorted to focusing on the northern hemisphere where there was most of the records. And they concluded that the 30 years prior to the publication of the report was the warmest of any 30-year period back to at least 1,400 years. So essentially, they showed that the temperatures of recent decades exceeded those of the medieval climate anomaly. But there wasn't sufficient evidence to really make an assessment about global temperature change. Since AR5, there's been some major efforts to develop larger data sets that extend globally. One of those efforts was organized through the Past Global Changes program, and a goal was to tap a greater variety of evidence from superficial archives for past temperature change. And so a large group collected data from over 690 sites. They were standardized and quality controlled, and they were used to, they were applied to several different techniques for reconstructing past global temperature changes. So rather than different studies, what we see in the different colored lines are different statistical approaches to that were applied to the same data set with different screening criteria and different assumptions, different strengths and weaknesses, essentially to compare the results from different methodological choices. And in each case, so for these 7 different methods, each one used the observational evidence for the last 170 years of temperature based on instrumental data. And so this gives us a more global view, a picture that is based on a greater variety of archive types. And I wanted to add to that a recent study, Cuesta Valero published on ground temperatures that were based on sort of geophysical inversion models of temperature profiles globally that reinforces the temperature, at least the median of the ensemble of the 7 different methods that were used for this reconstruction fits nicely with the ground surface temperatures, which was based on independent evidence. I'm also showing the last decade, which is seen over a degree of warming relative to pre-industrial time. And so from this perspective, we can update the previous assessment report to say that recent decades were more likely warmer than any time, any other decades during the last 2,000 years. So that takes us further back. How far back do we need to look before we find a time that's been as warm as recently? So in 2019, there was a big push by a number of us to extend the reconstructions further back in time, building on the lessons from the 2K project. We assembled data from over 800 different records. And the colors on the map show the various archive types and the distributions of the site. And essentially, we used the 2K reconstruction as a target to help train the reconstructions, again, using a multi-method reconstruction approach to develop an ensemble of plausible temperature changes. And 90% of those ensembles fall within the blue band. So this reconstruction shows peak temperatures in the middle part of the Holocene, going back here 12,000 years, with temperatures averaging about 0.5 degree warming for the median reconstruction. Well, there's a new reconstruction for the Holocene, well, actually extending back through the last glacial maximum that is available now as a preprint. And this is based on a new approach to data assimilation, where information from climate models is blended with the proxy evidence to create a reconstruction. And this one shows, by the way, this is Osman and et al.'s reconstruction, and it shows essentially no Holocene global thermal maximum. And so I think, regardless of which of these is correct, or whether the answer is somewhere in between, I think we can say that the recent decades were probably warmer than any time during the present interglacial period. So we need to look even further back. This graph shows temperature history through the Cenozoic. It's on 3 different timescales, extending back 60 million years to 1 million years, and then in this timescale, from 1 million years to 20,000 years, and then the third is from 20,000 years on. So these are various published reconstructions. The older ones are further back in time. Those are based on various transformations of foraminifera records. So just to orient you here, the previous figure is in this box here in the Holocene. So from this perspective, we can see that sort of the next older candidate for period as warm as present. It would be the last interglacial, when temperatures were in the range of 0.5 degree to 1.5 degrees warmer than now, when sea levels were in the range of 5 to 10 meters higher than now as well. While I have this graph, I also wanted to provide a perspective on the projections of future climate change, the scenarios that Anna had talked about. So this shows the projections out to the end of this century and the end of 2300. And I've just shown the whole range here, from a low emissions scenario to a high emissions scenario. And I wanted to note that the range for 2100, well, in the middle of that range is approximately 3 degrees centigrade. And temperatures of that magnitude, we need to go back to the mid-Pliocene in order to find temperatures of that level. So sorry, let me go back here. I also wanted to make the point that even with aggressive reductions in emissions, the global surface temperatures are going to be at least 1 degree higher than pre-industrial for many centuries to come. So I think when we're thinking about recent warming, we don't want to just stop in 2021. We need to consider the long-term commitment. And I think in this respect, when we comparisons between the recent decades and the deeper past are on a lot firmer ground when we include the centuries, if not millennia, of commitment that we're facing for future warming. All right, so now moving on to reversing of the temperature as another sort of means, another characteristic of the unusualness of recent warming. I'd like to start with, well, something that Paul explained nicely with some nice illustrations about the Milankovitch theory of quaternary ice ages. You know, the basic tenet is that boreal summer insolation is the primary control on glacial inception. And this graph shows the insolation at 60 degrees north in the summer. At the top of the atmosphere, of course. And so, from the Milankovitch theory, first order, we would expect that that global glaciation would follow that path. Of course, we've already heard a lot about the variety of forcings and feedbacks that are also at play, including greenhouse gases, volcanic activity, solar activity, land use, land cover, dust, and more. Here, I'm just going to focus on the important forcing involving the amount of Northern Hemisphere ice cover as an important effect on albedo. Which is increasing downward on this scale. So essentially, I just want to make the simple point that when we combine in a simple linear way the feedbacks and forcings associated with ice albedo in the early part of the Holocene, along with Milankovitch forcing, we see the expected result that there's sort of a peak in around 7,000 years ago, after which the ice cover stabilizes and temperature trends, if they do follow that forcing, would decrease during the rest of the Holocene. And we see that very same pattern in the extent of glaciers around the globe. So I'm focusing here on mountain glaciers that are distributed around the world, and well, there were 189 time series that were summarized by Solomina and others. And I've simply created an index of their relative extent, and I've combined them into 4 major regions: the Arctic, Eurasia, low latitude, and Southern Hemisphere. And they all show, essentially the least extent at around 8,000 years and advancing towards the present, culminating in the Little Ice Age. So far, I've really only considered evidence from the surface, but of course, the oceans store the vast amount of the heat energy of global warming, and so it's appropriate to look at some depth as indicators as well within the ocean. There's a lot of studies to choose from. I'm choosing here to illustrate 2 prominent studies, one from Pacific intermediate water and another one from, well, essentially the world's ocean, showing the temperatures of bottom water. So Rosenthal and others used strategically located bathymetric transects, where they argued that they could sense temperature changes over large water masses at intermediate depths. And they found that temperatures cooled through the Holocene in those records. Shakin and others use global compilations of both benthic and planktonic foraminifera to isolate the temperature component of Del 018 in the bottom waters. And again, showing cooling after 8,000 years ago. Going back to the temperature 12K data set, we can subdivide the records into different proxy types, and all of which are supported by a healthy number of records, again, globally, all showing cooling since around 6,000 years ago. We can divide the same data set up into latitudinal bands, and in this case, 30-degree latitudinal bands, and we see that all except the southern polar region shows cooling through the middle and late Holocene. And the same is true for the 2,000-year data, which is again based on annual scale resolution that's calibrated to instrumental records that always show that the first millennium of the Common Era was warmer than the second millennium. Okay, then moving on to the rapidity of recent changes. I'm showing here some evidence from sea level change. So sea level is a great integrator of planetary warmth, but it does lag surface temperature. And there's challenges to teasing apart the influence of local variability with the global. This is one prominent study that was based on a variety of proxy evidence from salt marshes in northeastern North America, where they separated the global from the regional component of sea levels change and found that the most recent 100 years, when sea level has risen by 30 centimeters, was the fastest pace over this record of 2,500 years. So it's the 30 centimeters is 100 years is rapid, but of course we're reminded that the geologic evidence shows us that there are times of rapid change as well, including when there's a lot of glacier ice and meltwater primed to discharge to the ocean, and sea level rose at the pace, at least an order of magnitude of what faster than what's happening now, up to 5 meters per century. In terms of rapidity, we can also essentially investigate the time series by the 2K reconstruction. What I've plotted here is the running mean of the 51-year average across the Common Era. And we can see that during the last century, the rate of change in terms of the 50-year averages is unprecedented within the last 2,000 years. The same data set from pages 2K was used by Newcomb and others to develop a field reconstruction, so a mapped view of temperature around the planet. And they used this to demonstrate the sort of spatial uniformity of the present day climate change, present day temperature change, I should say. And so, they've essentially chunked out 3 major intervals over the last 2,000 years, each one that included some historical evidence for warm periods. So for example, the medieval, they've chosen a broad 5-century long period between the 18th and the 14th century, and found the 50-year period, found which century was the warmest 50-year period. And for the most part, it was the 10th century, but we see that warming occurred at different times in different places. And that's very different than recent warming. When we look over the whole Common Era, the warmest 50-year period took place in the 20th century. So another way that the present warming is unusual is the sort of the global synchronicity and homogeneity of the warming. And we see that as well in terms of the glacier evidence, again, around the world. In the first millennium of the Common Era, there were dozens of glaciers advancing during any half century, culminating in the most extensive ice during the Little Ice Age. And essentially in the last 50 years, there's only been a few recorded glaciers that have actually advanced. All right, so is the current warming unusual? I would say yes. We have multiple indicators of global warming in the atmosphere, in the oceans, in the cryosphere that are reaching levels, and they're changing at rates that are unseen in many thousands of years or longer. And in terms of the atmosphere, I haven't discussed greenhouse gases, but obviously that is an important indicator of our global climate. And there's wonderful records that are emerging about major progress in documenting the past changes in CO2 over the Cenozoic, and they really reinforce the conclusions of this presentation. All right, so I feel like it wouldn't be complete without mentioning sort of a fifth and maybe most important way that current warming is unusual.
Really sorry, Darrell, but we're sort of running out of time for questions, and I think it would be really nice to have some questions. So if you could sort of wrap it up in this fifth point as quickly as possible, that would be wonderful. Thank you.
I will. Yes, thank you for that, Dan. So I just wanted to make the point that it's happening, the current warming, and unlike previous changes at a time when the effects are incurring on top of other stressors. And yeah, so it's a kind of a heavy point to end in this talk, but I think it's sort of worth reiterating the theme of the symposium, and that is the long-term perspective on climate change is really essential when we're addressing the issues of facing humanity. So thanks to the authors of the papers that I presented here, and thanks to the group who helped pull together the temperature 12K data set. And I'll be happy to answer questions.
Great, that's fantastic, Darrell. Thank you very much for a wonderful overview of all the the indicators that we have of recent warming compared to longer term change. That's really great. So thank you, Darrell. So several of the questions, sort of all on a similar theme, sort of wondering whether in a lot of the comparisons you have are with paleo data with the recent record. And the question is some of the paleo data at lower resolution and maybe sparser data? And so is it, when you do these sorts of studies and when other people have done these sorts of studies, do they take account of that fact, if you like, that difference in temporal and spatial resolution between the recent record and the paleo data that you're comparing with?
Right, no, that's a great question, for sure. So I think the question of resolution is always important to consider. I think that looking into future changes is a really important part of that perspective. Being able to consider a larger period of time over multiple hundreds of years, and thinking about our commitment into the into the future that way. So resolution is an important effect.
Yeah, I guess another way of putting the question, if you went 1,000 years in the future and people geologists were looking at our current warming, would it stand out as unusual compared to 1,000 years before, if you like?
Yeah. I mean, I think that for the most part in this presentation, I've really focused on those records that are resolved at annual scale when looking at the last 2,000 years, and I think for the Holocene, I've sort of focused on those records that have multi-centennial sorts of resolutions, and so
yeah. So we're sort of comparing apples with apples in some ways for some of the more recent comparisons, at least.
Yes. Yeah. Yes, that's right.
Okay. Thank you. So then Michael White has a question about the global mean surface temperature as a metric, and whether it is, is it the best metric to use given the the huge amount of heat in the ocean? Are there other things we should be looking at other than GMS2 that might be more appropriate for encapsulating the total energy in the system, for example?
Yeah, right. No, I mean, there's no question that the ocean stores the majority of the Earth's heat energy. I think that when we're looking at a longer time frame, that it makes sense to look at the processes involving the deeper ocean, including ocean temperature. But I think the response rate might be somewhat slower than the surface temperature itself, which would seem more relevant. I think that the global metrics do sort of obscure a lot of the regional variability, which of course is so important for thinking about the future and the effects of climate change as well. So I've really focused on the presentation on the global effects, but certainly we wouldn't want to discount the importance of regional variability as well.
Yeah. Great. Well, thank you very much. Thank you very much, Darrell. That's great. Really, thank you for answering those questions. And there are, there's a few more questions in the chat as well. I'd be really grateful if you're able to
great.
Have a look at some of those and maybe respond. That'd be fantastic. Thank you.
Be happy to do that. Thank you.
Thanks, Darren. And we've come to the end of this first session today, and I think it's been some really nice talks, really great presentations from our invited speakers and the early career scientists. So thanks huge amount to them, and thank you to them for answering the questions as well and doing a really nice job, I think, of answering those questions. It's been really good. So I think, well, actually, it would be nice. We don't, given that if people are people able to I don't think the audience are able to turn their microphones on. So unfortunately, we can't give all the speakers a clap as is traditional. But I'm sure I speak on behalf of everyone to say huge thanks to our speakers, and we are going to reconvene at UK time 4:45. So that's in about 20 minutes from now. So we'll have a break now. And we will have, after the break, we'll have Bette Otto Bliesner talking about how the geological record can be used to evaluate climate models. We'll have a flash talk from Pam Vervoort, and then we will have our plenary presentation from Maureen Raymo to finish things up, and where she will address the sort of all the themes, really, the whole, all the topics that we've been talking about in the context of what the geological record can tell us about the past and future. So I'll see you all in about 20 minutes. Thank you.
Good afternoon. Sorry, I didn't realize we were already starting. So my name is Babette Hoogakker. I'm a paleoceanographer based at Heydt University in Edinburgh, and I'm convening this session. So first of all, wow, it's been a really interesting first session about climate change in the geological record. There will be much more to come during this session, as well as tomorrow. So to emphasize, for our question and answer sessions, we would love to see some more questions from early career researchers as well. So again, please put your questions in the chat, and we will try and answer as many questions as we can live, although it might be that some might be answered subsequently. And before I introduce Bette, I just want to remind participants and speakers that we're all required to abide by the Geological Society London meeting and events code of conduct at all times. So anybody found to be violating this code of conduct would be permanently removed from the Zoom event. So our first speaker for session 2 is Dr. Bette Otto Bliesner. She's a senior scientist in the Paleo and Polar Climate section of the Climate and Global Dynamics Laboratory at NCAR. She's an internationally recognized Earth climate system modeler and has been extensively involved with the Intergovernmental Panel on Climate Change. Bette is a co-chair of the Community Earth System Model Paleoclimate Working Group, and she's also a member of the Scientific Steering Committee for the Paleoclimate Modeling Intercomparisons Project. Now, this group is very important. It coordinates international climate model experiments addressing past climate change and see how they are relevant to understanding future climate change. So Bette is giving an invited talk about how the geological record can be used to evaluate climate models. So over to you, Bette.
So thank you, Babette, and thanks to the Geological Society of London for convening this great workshop. I have the privilege of addressing one of the scientific questions in the statement and that is, how can the geologic record be used to evaluate climate models? And I think a good way of framing this question is to start from this figure that was just recently published by Ray et al. That shows atmospheric CO2, a kind of a paleo context. And it provides a context for what might be happening in the future. And I want to just illustrate here some of the changes in global temperature that go along with this record from some of the targeted periods that have had climate model intercomparisons or MIP projects. So if we look at first at kind of the early record here, the early Eocene climatic optimum about 50 million years ago, we have CO2 levels 1,200 to maybe even up to 2,500 parts per million, and global mean temperature anomalies or changes in warming of 10 to 18 degrees Celsius. And this is really quite comparable to what we might expect with the direst future scenarios. Admittedly, these anthropogenic changes are happening at a much faster time scale, but they show us the committed climate change that may be possible if we could sustain much higher CO2s similar to this geologic time period. We also have the mid-Pliocene warm period here, about 0.3 to 3 million years ago, where CO2 levels were actually quite close to what we're experiencing right now in 2020 of 414 parts per million, and global warming of maybe 2.5 to 4 degrees Celsius. Another time period that's been part of the model intercomparison of PMIP for a long time is the LGM, 21,000 years ago. Much lower CO2 and much colder temperatures, but still a very good time period to evaluate the sensitivity to CO2 in our climate models. And then I just want to point out the most recent interval, the time interval, as I will show you, that we usually use to develop our climate models, which fairly modest, but very concerning increases in CO2 from 360 to 397, and global mean temperatures warming by about 1 degree Celsius. Got to get my cursor to move. I'll just move it a different way. So just to start out first, though, before going into this topic, it's kind of important to know how we develop climate models, or what we call at NCAR Earth system models, because we're starting to include models that can simulate, for example, the carbon cycle, the ice sheets. And these models, as all of the MIP models that are included in the MIP, CMIP, and IPCC, are models that generally include models of the atmosphere, the ocean, sea ice, and land surface, but they're varying complexity and resolution. And as Paul mentioned, they're based on fundamental principles of physics like the Navier-Stokes equations, but they also need to include parameterizations of processes that are difficult to represent within the resolution of the models. For example, things like clouds and that. So those are based on theory and observations. And when we develop these models, we compare to a variety, a large number actually, of observations that we have for the instrumental period. Just shown on the right here is a figure that shows comparison of satellite observations of the forcing by clouds on the radiation balance. And then two versions of the model. The current one we're using now, CESN2, and our previous version that we used in the last IPCC. And these just show the biases or the anomalies. So you can see that in terms of this type of parameter, the current model, CESN2, is doing much better than CESN1. The other thing we do is we really want to reproduce the long-term trend of surface temperature anomalies in the 20th century when we have instrumental records. And so we will tune the model parameters within their range of uncertainties until we do get a reasonable match. And so what is just shown here is one of the experiments, which we call experiment A, that failed this test. why the model that we eventually adopted is in the red curve and compared to observations. Recall that our historical period is a fairly short period and really doesn't get to the extreme atmospheric CO2 conditions and greenhouse increases that we expect in the future. So what I'd like to talk about today is three different topics, starting out first with some of our model simulations with these newer models compared to newer reconstructions. We have a better understanding now of the climatic influences and non-climatic influences of on proxies, how climate indicators are recorded in these proxies. And we have new regional and statistical reconstructions now that we can use to compare to the models. I'd like to talk about some of the expanded evaluations that we can now do with new model capabilities, such as simulating ice sheets or actually simulating the isotopes that are recorded in the data. And then I'd like to end with some illustrations from our model. As Paul mentioned, we like to evaluate the models with the geologic record, kind of an out-of-sample evaluation. But what we're finding as we go to newer and more complex models is we may actually want to use these records to develop the climate models. So the first example I want to tell you about comparing model simulations to Pliocene data reconstructions is for the mid-Pliocene warm period, where remember atmospheric CO2 is fairly similar to what we have now. And this is some results done by Jess Tierney, where she did a new reconstruction using alkanone from 28 sites calibrated with the baseline calibration. And then looking at what the models reproduce in terms of the change in the east-west tropical Pacific gradient here on the y-axis and the change in the meridional SST gradient. And the proxy data suggest, is shown here in the pink box. And what you can see in terms of the models, particularly if you take into account their uncertainty intervals, is they do fairly well in terms of the change in the east-west tropical gradient and suggest a weakening of this gradient across the tropical Pacific. On the other hand, neither the data or the models suggest a permanent El Nino, which would be a threshold down here at about -3 in terms of the change in the SST gradient. But the models, we can also look at things like the Walker circulation, which is just a circulation in the tropical Pacific where you have rising motion in the Western Pacific and steepening in the Eastern Pacific. And there's been a lot of debate whether it will weaken in the future or strengthen. And the models and data here for the models that do quite well compared to the proxy data suggest that it'll weaken in the future. Another time period that's been a standard for the PMIP project is to evaluate the models in terms of at the LGM along with the data. This is time period again, which has a lower greenhouse gas concentrations and very large ice sheets. And so what is shown here is the evolution of the models from PMIP 3 to PMIP 4 in terms of the land-ocean contrast that they simulate of surface temperature in the tropics. And what you can see here is that there's quite a large range in the models in terms of the amount of cooling, both over the land and the ocean. Some models fit within the data reconstructions, which actually have changed to suggest stronger cooling for the land and ocean in the tropics as we go from, for example, the Bartline and the Margot simulations in 2011 and 2009 to the newer ones by Cleater and Tierney. And as I said, these reconstructions are also being updated. So here shows two more reconstructions, one from GLOMAP published this last year, and one from Tierney where she used some data simulations. And so you can see here that there's still significant uncertainties of the amount of LGM cooling over the land and the ocean in the tropics. I also point out here that as of yet, there's only a few of the newest models, the CMIP6 models, that have produced LGM simulations, and those are shown indicated by the boxes in the legend here. One other thing about data reconstructions, which is really going to be an interesting thing to evaluate models, is we're now using new statistical techniques to allow combining information from proxy data and model simulations. These are based on some of the weather-based data simulation techniques that are now being applied to paleoclimate data. So from this illustration, it just shows that we take proxy data information and you take the physics from the climate model and you balance those to come up with a global reconstruction, either of SSTs or even things that we really don't have proxies for, like change in precipitation, that are consistent with the proxy data and the physics and covariance of the climate models. We also have new model capabilities, as I mentioned, and one of the really exciting ones that has recently been included in more and more of the climate models is the simulation directly of water isotopes, which of course is important because that is what many of our measurements are of past climate change. And so it allows us a more direct comparison and a better interpretation of past changes. And this just shows an interesting study from Alexander Thompson, where he looked at the simulation of the deuterium of precipitation change and also in the soils. And he compared these to proxy records that were available that he compiled for both the Gulf of Aden and also in Lake Tana. And so he could look at the model simulations, and what he finds is that these are deuterium of leaf wax for these records, is that you really need to consider not only precipitation changes, but how water is stored in the soil and its isotopic composition, and then how that is evaporated from the models. So this gives being able to do these isotope interpretations gives us a much fuller way of interpreting the data and the responses. The other new model capability I just wanted to mention is we're now able to couple climate and ice sheet models, and the ice sheet models are becoming more sophisticated too. They're not just simulating the surface mass balance, the extent and the volume of the ice sheets, but also how the ice sheets flow. And so this is just a simulation that we recently completed for the last interglacial, where we force it with the orbital insulation anomalies 127,000 years ago to 119,000 years ago. And what you can say here is that the ice sheet retreats here, and then it reverses and it regrows as the climate cools here. And you can see that, the ice divide here, but also the strong flowing regions off the ice sheet at its edges. What was really interesting about this simulation too is we actually coupled it to a vegetation model, Biome 4, and simulated the changes in vegetation, which is very important because we know from the last interglacial that vegetation progressed northward, particularly in the Canadian region upstream of Greenland, with trees replacing tundra and shrubs also. And what we find is the ice sheet's very sensitive to this vegetation. We have a minimum of the ice sheet extent at about 122, contributing about 4 meters of sea level rise when we include it. But when we only keep the vegetation at its pre-industrial vegetation, the ice sheet only barely retreats and then recovers. And it's important to realize that this means that in our models, many of which that we're using now include land use changes, we also need to consider natural vegetation responses as we look into the future. And then the final thing in terms of new model capabilities, which is really important and is a big uncertainty looking into the future, is the treatment of clouds and aerosols. And I want to illustrate this by looking at the early Eocene climatic optimum about 50 million years ago. The early models that we had when we forced them with the very high CO2 estimates from proxies and compared to proxy estimates, we just couldn't get the amount of global warming or even the change in the equator to pole reduction in the gradient. And the only one model that eventually could do this was one published by Keel and Shields, where they changed the treatment of the cloud microphysical parameters so they could actually match the proxy records by changing substantially these to account for presumed aerosol concentrations in the Eocene. Since then, there have been other simulations, the CCSM4, which was in the last IPCC. A number of simulations were done at different levels of CO2. And it was only when you got up to 16 times pre-industrial values, or about 4,500 parts per million, that you could finally get the warming that the data suggests. Why the newer model, the CESM12, now seem to get into the sweet spot here of both CO2 forcing and global mean sea surface temperature. And key then is to think about what was different between these models. In particular, I want to show you some results from Jianzhu's Science Advances, where he looked at what was different between the atmospheric model in CCSM4 versus in CESM 1.2. And so what he found when he did a very detailed analysis here is that if he started looking at the differences between CAM4 and CAM5, it's when I changed the cloud microphysics shown here in the X's here, that he could get the reduction in low cloud cover that was important for this greater warming with higher CO2 in the early Eocene. So then just finally, I want to talk about what is happening now with the newest model. And we were so happy with CESM 1.2, and now we find the model that we're using in IPCC, CESM 2, overestimates the warmer temperatures of the early Eocene. And in fact, the hypothesis we have here is that as the ECS, the equilibrium climate sensitivity, has increased to now over 5 degrees Celsius for a doubling, that maybe this high climate sensitivity is too high. Further evidence of this is if we look at the last glacial maximum with low CO2, shown on the top here is the simulation of cooling as compared to proxy records in CESM1 versus CESM2. You can see much greater cooling in CESM2. And that's also indicated if we compare the proxy SSTs either in the tropics or the extratropics, which is what's simulated in the model. CESM1 in general, the proxy and the data agree fairly well. That's as indicated by this 1 by 1 line. Why CESM2 gets much colder temperatures, no matter which of the proxy records you look at, and whether you look at the tropics or the extratropics. So just the final slide then, and to convince you that maybe we need to start using geologic data for developing our models is the development of a new version of CESM2, which we've termed the paleo-calibrated CESM2. So what is shown here on the bottom is a proxy estimate of the global cooling as the simulation runs 100 years and its uncertainty. The The red line is the newest model, CESM2, which includes CAM6. And you can see it's way, way too cold. After 100 years, it's already more than 9 degrees cooling globally. Why, if we use CESM2 with the old atmosphere model, CAM5, it's not. And through a series of tests, Zhangzhou has attributed this to the cloud microphysical processes. He's looked at what's different between CAM5 and CAM6 in terms of the convection schemes, the microphysics schemes, and the ice nucleation schemes. And if he just changes the convection scheme, he still gets strong cooling, shown here in the blue line. But if he changes the microphysics or the ice nucleation, now he gets a much better match in terms of LGM global cooling as compared to the proxy estimates. We've actually developed a model which we call the paleo-calibrated that takes into account these changes in terms of ice nucleation and aerosols. So the cloud aerosol interactions are very important to be able to get this right, and yet they're the most uncertain when we're developing the climate model. So just to finish up, some reflections on this for understanding the geologic past. We have some new data reconstructions. We understand the proxy data in terms of its climatic signatures and how we can assimilate that. We have new model capabilities that allow us to look at things like ice sheets or isotopes. And we're also improving the parameterizations in the models. I'd like to suggest, and we really need to partner these together rather than doing one or the other. It'd be good to not only evaluate, but use our geologic record to develop climate models that provide the projections for the future. And then just to finish up here, I like this quote from John Kutzbach, a good friend, a mentor, a colleague who we unfortunately lost earlier this year. But I like it very much because it says climate forecasts suffer from the lack of accountability. Their moment of truth is decades in the future. But when the same computer programs are used to hindcast the past, climate scientists know what the correct answer to the test should be. So thank you.
Thank you very much, Betty. So we have a couple of questions. One is, that was a brilliant talk, by the way. Thanks very much. It's very good to see that cloud physics is important. I think people that used the Kiel model before have shown some similar results to that as well. So we got a question from Gavin Foster. He's very excited to see that the coupled ice models are coming online. And he's asking, like, how is this done as to be computationally efficient? Is the ice sheet simplified, or is the climate model?
So for now, the ice sheet models, at least the one we're still using simulating the Greenland ice sheet, or we're starting to simulate groups with North American ice sheet. And the key aspect of it is how we downscale to the ice sheet. So we still run the ice sheet at 4 kilometers, while the typical climate model resolution is more like 100 kilometers. But we can use a downscaling where we can look at different elevation classes and actually downscale within the climate simulation to get down to that resolution. To run long simulations, we also sometimes have to make some ways of getting it faster. For example, accelerate the ice sheet by maybe 10 years. So maybe 10 years we update it, which is still quite recent when you're thinking about a simulation that is that long. So yeah, I'm very excited. Antarctic ice sheet is going to be a little bit more difficult because it has ice shelves, but the greatest minds are working on that too. So I think that will be coming online, and then we can start to use it for deeper time, which would I think would be really fun.
Okay, thanks. And then there's a question from Matthew Status. So he's saying, have current climate models considered changes in cloud cover due to decreasing amounts of anthropogenic aerosols? And could this lead to future warming?
Yeah, aerosols are really in the important aspect and how the clouds interact with the aerosols. So we know they reflect and scatter radiation, but they also affect kind of the microphysics of the clouds. So the how thick or thin the clouds are. And so that's really important. And I think those aerosol cloud interactions are key. We found that this paleo-calibrated simulation, we actually could get the 20th century also right, even though it has a lower climate sensitivity, because of the aerosol cloud interactions had decreased. So I think there's a lot to learn about those interactions. And I think using the geologic record is going to really help us. So the LGM simulation I showed you, we're still needing to look more closely at the aerosols that we include.
Thanks. So there's more questions, but I'll just do a final one from Dan Lunt. And then if you don't mind answering the questions online afterward, that'd be wonderful. So Dan is asking, so when studying past changes with models, is it better that we focus on using lower complexity models that are less accurate, but they can be spun up to equilibrium? Or should we be using the very latest model that may not be up to full equilibrium due to time and being more expensive?
I mean, I think it is, you have to balance that. I think we do need to use the higher complexity models because those are the models that are being used for the future projections. So we really need to show, for example, with our LGM simulation, we had to convince those that are doing future that, yes, there is a problem, that yes, the data is uncertain, but these are large changes and we're way outside that. But when you want to do really long simulations and want to look at, for example, glacial, interglacial cycles, we may want to use lower complexity models to do that. So I think it's a balance between the two that we need to do.
Thank you very much. Thanks very much for a really inspiring talk. So our second speaker of this session too is Pam Vervoort. So Pam is a PhD candidate at the University of California, Riverside. And she's interested in a whole bunch of things, including paleoclimatology, carbon cycling, astronomical forcing, paleoceanography, orbital cycles, and Earth system modeling. And her current research centers around astronomical climate forcings using numerical modeling. So today she will be presenting her work on negative carbon isotope excursions and interpretative framework. So Betty, if you could turn your screen off, and then I will turn mine off as well, and then Pam can take the stage. Thanks.
Great, thank you so much for the introduction. So today I'd like to take some time and talk about negative carbon isotope excursions in the geological record, because they provide an incredibly valuable source of information where we're trying to understand how the Earth has responded in the past to past carbon perturbations. So NCIEs in the geological record are produced by the release of isotopically light carbon to the ocean and atmosphere. But there is some complications that make the interpretation of these negative excursions more difficult. First of all, in the past, we don't really know the mass of the or the source of the carbon that was released during past events, which means that according to simple isotopic mass balance, there is multiple possible combinations that produce the exact same NCIE of isotopic masses and sources. So we generally tend to turn to modeling to relate the magnitude of the carbon perturbation to changes in temperature or carbonate chemistry that are recorded by proxies to better understand the past climate sensitivity. But then still relating the amount of carbon input to changes in CO2 is not per se straightforward by long-term carbon cycle feedbacks that produce nonlinear relationships between the two. Also, the simple isotopic mass balance equation doesn't account for these time-dependent processes. Finally, also an important problem is that there's often a lower resolution of the H model due to perturbations in the environment, which makes it difficult to determine whether it was a rapid or a slow carbon release event. So we really wanted to come up with a framework that goes beyond simple isotopic mass balance and does consider the recorded environmental changes and also accounts for long-term carbon cycle feedbacks. So in the Earth system model, we simulate over 400 different carbon release scenarios. Each of them have different durations, different carbon sources, different NCAE sizes, and also 9 different shapes. So in some occasions, we have a scenario where the onset is very rapid and sometimes it's very slow. So on this slide, I'm showing some general trends of the framework itself. The left-hand side shows the carbon forcing that the model calculates that is required to produce, in this case, a 0.5 per mil negative excursion, although the patterns are the same for any of the NCAE sizes. Each marker is an individual different simulation depending on the onset duration of an event and the source.
Pam, really sorry to interrupt. I think I'm not sure if we can see your slides actually.
Oh. Let me share. Oh, yeah, you're absolutely right.
Sorry.
No, yeah, you're fine. So
thank you.
Yeah, back to this slide. I assume you can see it properly now.
Yeah, it looks good now.
Yes.
Okay, perfect. Yeah, so back to the forcings here. So this one shows the carbon forcing itself that the model calculates to produce a certain 0.5 per mil NCIE, depending on the onset duration and the isotopic source of the carbon that is released. So for the longest onset durations, you'll see that more isotopically light carbon input is required. But essentially, the impact on the change in the atmospheric CO2, ocean pH, and sea surface temperature is mitigated for longer duration events compared to the shorter events. And this is consistent with the traditional view that global warming leads to enhanced weathering, and weathering actually adds isotopically heavy carbon to the ocean. So more isotopically light carbon input is needed to sustain these negative values over prolonged periods of time. But simultaneously, weathering also removes CO2 from the atmosphere, so the environmental impact is mitigated for the longer event durations. Secondly, also, I want to point you to this decoupling between the ocean pH and the saturation state for the longest carbon release events. And it is possible that for the longer events that the ocean pH changes quite a bit in response to carbon release, but that there's virtually no change in the amount of calcium carbonate saturation in the ocean. And because the saturation state of the ocean determines how much calcium carbonate is preserved, you might actually end up in a situation where the surface ocean pH is low, but there's virtually no change in calcium carbonate dissolution in the ocean or preservation. So theoretically, with proxy data for ocean pH and the saturation state, we would be able to better constrain the onset time of a carbon release event, because those two are time-dependent processes. Okay, so I quickly want to move on to an example showing the Eocene thermal maximum 2. It is part of a series of hyperthermal events across the early Cenozoic. In the geological record, it is generally characterized as a 1 per mil drop in delta 13C values, 1.5 depending on where you're looking. Proxy records also indicate a sea surface temperature rise of about 3 to 5 degrees Celsius. There is drop in pH and widespread calcium carbonate dissolution. So here is a different way to visualize our model framework. On the y-axis here, you see the different NCIE sizes that we simulate. So for the EETM2, we're only interested here in the 1 per mil NCIE that I want to direct your focus to. And on the x-axis is NCIE onset duration. So for EETM2, it would be a 25 or 50 kiloyear onset duration according to depending on which age model you use. So the way to read this framework is, let's assume this 1 per mil NCIE would be driven by a volcanic or mantle-derived source. The sea surface temperature rise would be about 4 degrees Celsius. But if that exact same NCIE would be driven by biogenic methane, the increase would only be 0.4 degrees Celsius, so much lower. Based on this, only on this information, and proxy records. From a first hand, you would suggest that a volcanic source matches best at what we find in the records. We can do exactly the same for the surface pH, and our framework suggests that once again, a volcanic source is the most likely source to produce the EETM2. But it's not quite consistent with what we already know about Eocene hyperthermals because they're orbitally paced. So this volcanic source is not consistent with the orbital pacing. That's why generally people assume the 1 per mil NCIE produced by isotopically light methane or perhaps organic carbon. But according to our model, this doesn't result in the changes that are recorded by proxy records. There's not enough temperature change, not enough calcium carbonate dissolution, which means that either the initial NCIE was much greater than the 1 per mil that is preserved in the records, or the onset was actually much shorter than what we know. So I think this is a good way to see how the records can be, the framework can be used in different ways. I'm definitely running out of time, so I'll leave this slide up and I'll take any questions.
Thank you very much, Pam. That was a great presentation. So these simulations were run with Genie?
Yes, yeah, they were. Intermediate complexity Earth system model.
Yes. So if I'm correct, Genie doesn't really simulate organic carbon very well, or hasn't got it in the sediments, right? So could this have an impact on your interpretation of these negative carbon isotope excursions?
Definitely. So Genie can actually simulate organic carbon burial, but it is not included in the simulations here. Okay. So this is basically the same as assuming that there is no variation in the amount of organic carbon burial or removal throughout the event. But it is also not very straightforward to simulate this because the response to the amount of organic carbon burial is not really well known. We don't really have evidence throughout NCIEs how exactly organic carbon burial changed on a global scale. It's difficult to find geological evidence of this. So we really wanted to come up with a more general framework. Organic carbon burial for an NCIE could increase in one location, but that doesn't mean that it increases globally. We do have plans, however, to include variable organic carbon burial, but to do this properly, we would also have to assume, we would also have to include temperature dependent, expert productivity, temperature dependent, organic carbon remineralization to really get a full sense of how organic carbon responds throughout the system. So perhaps there is enhanced release of enhanced burial of organic carbon, which would mean that we actually have a lower estimate of our carbon perturbation for each of the NCIEs. So definitely stay tuned because we do tend to expand our framework essentially.
Right. Well, thanks very much, Pam. That's brilliant. So if you unshare, then I'm going to introduce. Would you mind also turning your video? Thank you. That's brilliant. So our third and final speaker for session 3 is Professor Maureen Raymo. So Mo is a paleoceanographer, marine geologist who studies the history and causes of climate change in Earth's past. And she already knew by the age of 8, I believe, that she wanted to be a paleoceanographer. So Mo was the first female recipient of the Geological Society Wollaston Medal. And this is the highest award that the Geological Society gives out. And it's given to geoscientists who have made a significant impact through their research. So Mo is an outstanding scientist who's been setting the agenda and research in the history of the ocean and the Earth as a whole for 30 years. And she'll be given our plenary lecture, which is titled, What the Geological Record Tells Us About Present and Future Climate. So please go ahead, Mo.
Thanks, Babette. Can you hear me?
Yes.
Yeah, okay, I'm going to share my screen. And hopefully this will work perfectly. Do you all see my screen?
Yes, it's great. Thanks.
Wonderful. Well, thank you, Babette. And I'd also like to thank Dan Lunt and the rest of the organizers of this conference for inviting me to speak. I'm really honored. Even more importantly, I really applaud the statement released by the Geological Society on climate change, and incredibly important. And of course, climate change is the defining challenge of our generation. How we grapple with, mitigate, and adapt to this global challenge today will determine the challenges that your and my children and grandchildren will face decades from now. And I have a very real sense of humanity being at a tipping point. And as climate scientists and earth scientists, I think we all know what that means. We have a future that could be very bright, or it could be very devastating. And I think many of us find it emotionally exhausting sometimes to think about, especially now on top of the immediate crisis of the pandemic. However, onward. I can't move forward. How am I moving forward? Hold on. Is that, oh, why can't I move forward? Oh, okay, that worked. So in my talk, I'm going to focus on on a very high level of what can the geologic record tell us about climate change and the stability of polar ice sheets. And I mean, this is really the question that's defined my entire career thinking about this. But more to the point, I think another way to rephrase that is what is likely to happen as we continue to dump carbon dioxide, which is essentially a pollution product, a clear odorless waste product, into the world's atmosphere. And on the left is a flask somebody gave me of the last time atmospheric CO2 was below 400 parts per million in the atmosphere. And I really hope I live to see the day when I have another flask with a new date on it that also says less than 400 ppm CO2. We'll see. So I'm sure all of you are familiar with this curve. The Keeling curve is probably the most famous paleoclimate curve of all time data set. I'm calling it paleo just because it's historical. And of course, this is the inexorable rise of CO2 in the atmosphere due to the combustion of fossil fuels primarily. And there's so much about what's gone on in the last century that has been put in stark profile or by looking at what is going on now in the context of the geologic record. And in particular, we can see that that curve that I just showed you is this solid red line right here at the very end of this curve. And it's just so clear that what humans have done in the last century and a half is just extraordinarily unusual on geologic timescales. And of course, you know, recognizing this, that we're doing this, you know, we're well past arguing about that we are the source of CO2 to the atmosphere. The next obvious question is how important is CO2 in controlling Earth's climate? And, you know, for instance, the Earth does seem to be warming. Is that coincidental, causal, etc.? We know that these are, you know, huge debates that are still going on outside of the scientific community, not within the scientific community. But I do want to address this question kind of straight on. And really, you know, this is a question that is can be approached from a both physics standpoint and from an earth science and climate science standpoint. And I'll just start by thinking about it fundamentally as a physics problem. And, you know, we know that the climate system is incredibly complex. We've just seen so many talks that illustrate that. And yet, despite that complexity, we also know that the Earth is basically just a giant rock orbiting a sun, a star that is giving out energy. And if you ask the question, what controls the Earth's average temperature? It's actually a really simple physics problem. It's, you know, typically the radiation chapter of a freshman physics textbook. And if you want to think about the Earth's climate at any time in the past or the future, there's basically three three variables you can play with. You can play with the amount of solar radiation received at the top of the Earth's atmosphere. You can play with the Earth's reflectivity or albedo, how much is reflected back to space and lost, either through reflection off of land, snow, ice, particles in the atmosphere, etc. And then there's the greenhouse gas knob, and that's obviously the knob that we have cranked up. And so this role of CO2 in climate in the geologic record was clearly started out as a theoretical problem long before it was an observational problem. And indeed, even when I started studying climate in the late 70s, CO2 proxies, CO2 records of, beyond the realm of the Industrial Revolution were just coming out in ice cores in the late 70s and early 80s. So really geologic scale CO2 records that you could then compare to climate change over ice age cycles. And then longer term, of course, now, it's really in the last 2 decades, we have geochemical proxy records of CO2 going back almost to, hundreds of thousands, hundreds of millions of years now. So we know, just again, stepping back big picture, we know that on every time scale we look at Earth's climate, we see these same 3 knobs operating to control climate, especially with respect to CO2. We know on the time scale of the Cenozoic that as we go back in time to the Eocene, for instance, the poles were dramatically warmer. There's many, many lines of evidence for this, but probably the most intuitive just are the giant animal fossils and vegetation fossils that are found at the poles at that time. And we are beginning, and I really do believe we're just beginning to unravel a really in-depth understanding of how CO2 cycles between the Earth's interior through the silicate weathering cycle, through the carbonate weathering cycle, through the organic carbon burial and oxidation cycle, through the cycle of mid-ocean ridge and off-ridge basalt weathering in the deep sea and how that impacts ocean chemistry and therefore atmospheric chemistry. But we do understand that there is this geologic carbon cycle that is causing CO2 in the atmosphere to go up and down, and climate is obviously responding to that and warming and cooling. Now, just again, as context, we do know that if we stay on the same trajectory we are on right now in terms of global carbon emissions, greenhouse gas emissions, we will be at the Eocene level by 2100. Obviously, you might use the metaphor of a suicide mission for a planet if we stay on that trajectory. So again, this comes back to that angst that we really hope that the whole world just wakes up and tackles this problem with the utter laser focus that it deserves at this point. I also put on this figure a little oil rig right here that obviously is illustrating the fact that we're completely bypassing the geologic carbon cycle right now and taking CO2 out of the deep Earth's interior and put it into the atmosphere at a rate that's like almost more than an order of magnitude higher than the natural rate of volcanic degassing. So we also know from the geologic record that on timescales much shorter than the geologic timescale of the carbon cycle, the plate tectonic cycle, but on timescales of tens of thousands of years, we do know that the Earth's climate is also varying dramatically. And Ayako, I saw you out in the audience. This is a video from a paper that Ayako published in Nature in 2013. And it's showing how the subtle variations in the Earth-Sun distance due to Milankovitch orbital variations are enough to drive the Earth into and out of these giant climate cycles of the ice ages. And as you know, where we are now, we would have been going back into an ice age. For better or for worse, we may have already thwarted the next ice age. This is the early Anthropocene hypothesis of Bill Ruderman. And humans now control the climate of our planet, albeit quite quite imperfectly at the moment. And people often ask me, when will we have another ice age? And my answer is often never. We will not have another ice age as long as humans roam the planet. So we do understand, again, the knobs, the relationships between CO2 and climate. Trying to get to my next slide. There we go. And it really comes back to the present. And why do we care about what we know? And how does it inform us going forward? Well, I really think the biggest question facing us right now is this one of how sensitive are ice sheets to a modest global warming. And by that, I mean 1 to 2 degrees Celsius relative to pre-industrial. So we've already warmed by 1 degree. We're well on our way to 2 degrees. We have these giant polar ice sheets located at the poles that are the fastest warming parts of the planet. If you melted all the ice on Greenland and spread it evenly over the planet, it would be 6 meters of sea level rise. Same for the West Antarctic ice sheet, and 55 meters of sea level rise for the East Antarctic ice sheet. We know that the ice sheets are melting. The sea level has risen by about 8 inches globally. Sorry, just use this slide in America. 20 centimeters globally on average. Some places are much higher. It's about a foot around where I live. I guess that's about 30 centimeters. And while early on, much of this rise was due to thermal expansion, increasingly the rise is due to the melting of the polar ice sheets. And we know not only is sea level rising, and this is tide gauge data with this little black bit tail at the end being satellite data. We know that not only is sea level rising, but also that the rate of sea level rise is accelerating. One of the other really cool things that we have learned about sea level over the last decade or so of sea level studies is this now widespread recognition that the oceans aren't a bathtub. The sea level is not going to rise and fall everywhere the same. There could potentially be winners and losers. And I'll just explain quickly what this slide means. If you had 1 meter of sea level rise, and that meter of sea level rise came from Greenland, everywhere that's red, sea level would fall, and everywhere that's blue, sea level would rise, and it would rise by 1 meter, where it goes from light blue to darker blue. And when you're down to this darkest blue, it rise by 1.5 meters. So that's what this scale bar on the right means. And vice versa, if you have 1 meter of sea level rise from West Antarctica, you can see how that sea level rise will be manifest around the world. So here in New York, where I live, or actually I think this is pointing to Washington, DC, for obvious reasons, it's going to be far less painful if Greenland melts versus whether West Antarctic melts. So this is a wonderful thing to try to extract from the geologic record. What do we know about the histories of the individual ice sheets? Of course, in Great Britain, again, I think you're going to be happier if Greenland's melting than if West Antarctica is melting. So nowhere is the ice melting faster than in West Antarctica. And this is a map of Antarctic mass loss in gigatons from about 2006 to 2013, I believe. And you can see the huge mass loss around the Thwaites Glacier and Pine Island Glacier, et cetera. But what I find really interesting about this map, and the error bars are quite large right now on, what is the net mass change in the ice mass in Greenland through, in Antarctica through time. But what I find really interesting about this figure is that there's vast swaths of Antarctica that are gaining mass. And we understand this complexity. We understand that as you warm certain places, there's going to be more moisture and more snow and more ice accumulating. But it also translates out into the real world as part of this debate about, maybe gains in ice in certain places will offset losses in other places. And so this brings us back again to Can we model the future? Well, I would say that ice sheet models right now are improving every decade and need to get better and better. Some of them are now calibrated against the paleo record. So my kind of bias as a geologist is that the most important way to get at this question is to try to look at the geologic record and ask, what do these ice sheets do? What did these ice sheets do in the past with modest global warming? Now, I could talk for 2 hours about that, but I won't, obviously. And but I will ask the question, how do we construct sea level in the past? There's various methods, none are perfect. It's a very fascinating field of research at the moment. And but I will say that I think our best bet at getting towards an answer of past sea level is looking at the fossilized remains of shorelines in the past. And I'll just give 2 examples here. Is a Pliocene outcrop on the left with fossil barnacles on top of fossil oysters that look like they were buried yesterday, quite frankly. And then over here is my grad student, Mike Sandstrom, and he is standing on the top of an Eemian fossil reef in Western Australia. And so many people are doing these studies around the world. And this is a summary figure from a paper that I co-authored with Andrea Dutton and colleagues a few years ago. And I want to just focus on the Eemian, the second column from the left here. And it gives an estimate of how much higher sea level was at that time based on these different studies indicated by the initials and dates on the right. And the best estimate cited in IPCC for the Eemian is that sea level was 6 to 9 meters higher than at present. Okay. Temperature was 1 degree C warmer than pre-industrial. Now, this was not because CO2 was higher. CO2 was approximately the same as pre-industrial. It was because insulation at high latitudes was stronger due to the precessional cycle. So how good is this number? I'm going to just give you one more data figure here. And this is a sneak peek at a paper we hope will be out soon. It's in the final stages of review at PNAS. And this is a new estimate of what sea level was during the last interglacial. And it's from a broad mapping of sea level gradients across the Bahamian archipelago, which is on the peripheral bulge of the Laurentide ice sheet. And so the big advance here is it includes a probabilistic assessment of GIA models and narrows those GIA models down to ones that fit the data. And I will say, just as an aside, because someone may be interested in this, the GIA models that fit the data best are the ones that use a larger Fennoscandian ice sheet and a smaller Laurentide ice sheet during stage 6. But the big message here is that sea level during the Eemian, going from left to right, was much lower than 6 to 9 meters in our fieldwork and analysis. And in fact, instead of 6 to 9, we're quoting 1.2 to 5.3 as the likely peak sea level during the Eemian. Okay, so what do I know for sure? Climate is changing naturally all the time. We know that from the geologic record, and we can see over and over and over that small variations in incoming solar radiation, in Earth's albedo, and greenhouse gas concentrations lead to large and sometimes rapid changes in temperature, in ice volume, and sea level. We know at the end of the last ice age, sea level was rising at rates of 4 meters per century. I mean, that is phenomenal. And knowing everything we know about the history of Earth's climate, it's really true that you cannot escape the conclusion that the activities of 7 billion people are warming our climate. Okay, so this brings me to Lamont, my scientific home. You all have your scientific homes and our roles as scientists at this moment in time. For most of the 20th century, scientists at Lamont, and indeed all of us across the planet, we basically published papers in journals that were read by other scientists. as it became clear that climate change was real and was going to have potentially devastating impacts on the Earth and its sustainability, more and more of our work got translated into forms that could inform the public. First, through professional organizations, they increasingly took the role of translating our results for policy and broader education purposes. Of course, there were textbook writers and media stars such as Richard Attenborough, Carl Sagan, and others. Then we got to the IPCC reports. Many of the people at this meeting, I'm sure, have been involved with the IPCC efforts that have been so critical over the last few decades. There have been books on climate change in the popular literature, more reports. And I think all of us as scientists engage more and more with what we call here as broader impacts and also climate communication. But now we're reaching a watershed moment, I think. I think climate change is now impacting nearly everyone in the world in some way. It's really hard to escape the impacts and the reach of climate change nowadays. And this is forcing communities from the largest cities to the smallest villages around the world to engage with the problem of how to mitigate and how to adapt to the changes that are happening around them. And some of these challenges are obvious and others are less obvious. But if I look around Lamont now and look at what people are working on, here, these are all the problems I see our scientists working on, in addition to kind of much of the classic climate studies that have gone on before that were written on the previous slide. Our scientists, we're trying to predict hurricanes, monsoons, we're studying sea level rise, El Nino, ocean acidification, ecosystem and ocean health, and wildfires, droughts, so much more. And these are all Earth science and climate problems, but they all share a common theme. And that theme is people. These are all subjects that directly impact people's lives and livelihoods in ways that, in many cases, are being exacerbated by global warming. Haven't quite figured out if global warming is exacerbating earthquakes, but maybe it is. Who knows as ice sheets melt. Earthquakes are causing ice dam breakages in the Himalayas. So really, there's so many ways these different subjects are impacting people now. And in every community, all these billions of people around the world, they need to make decisions on how to mitigate and how to adapt to these changes. So I'll give you one example. Each coastline in the world is facing unique challenges. I mentioned earlier the Earth is not, the ocean is not a bathtub, right? Each coastline is different. The sea level will depend on where it is geographically, its proximity to the poles, on ocean temperature and circulation, on land movements, on the type of rock that the community is situated on human activities, and so much more. How will, on the upper right is Male, the capital of the Maldives. How will many of the Pacific Island nations survive a meter or two sea level rise? Venice has been struggling with sea level rise for centuries, and we can see how well they're doing by this picture. Miami is such an interesting situation. They got plenty of money. They would build walls if they could, but the rock of Miami is porous limestone, and so the water seas are rising up through the bedrock, actually. So they, instead of investing in walls, they invest in pumps, or they just pump the water into the ocean as it comes up through the ground. So the point is just that, how does every community deal with this level of both specificity to their unique challenge and the complexity of the climate impacts that they are experiencing? So all of these challenges are grounded in Earth and climate science, but they require a new way of doing science, a new way of creating and disseminating knowledge, and of collectively making decisions that are needed to move to a more sustainable future. And this brings me to the last point of my talk, the co-production of knowledge. Emerging globally is a new vision for how science and research is undertaken. Probably, I think it's probably maybe 2 years ago when I first started hearing about co-production of knowledge. What is it? Here's a definition that I like: an iterative and collaborative processes involving diverse types of expertise, knowledge, and actors to produce context-specific knowledge and pathways towards a sustainable future. Here's another figure that came from a beautiful article that was published last year. What is co-production of knowledge? First of all, it situates the process in a particular context, place, or issue. Miami, Arctic sea ice, communities. It explicitly recognizes that there are multiple ways of knowing and doing. There's scientific knowledge, there's local knowledge, there's traditional knowledge, there's indigenous knowledge, many perspectives. The problem is approached in a very goal-oriented way where a community working together articulates clearly defined, shared and meaningful goals that are related to the challenge at hand. And finally, the process allows for ongoing learning among actors, active engagement, and frequent interactions. And I want to just share in ending 2 examples from my colleagues at Lamont right now. The first is a project called Greenland Rising that is funded by NSF, Navigating the New Arctic Program. And that is led by Kirsty Tinto, Robin Bell, Jackie Osterman, and collaborators at the Greenland Institute of Natural Resources. And what they are doing is working collaboratively with local communities in Greenland to approach the sea level problem. And it's a collaboration that puts the needs and knowledge of the community at the heart of the project. And there's just some lovely pictures you can see around the sides. I particularly like this one in the lower left of 2 Greenland students acquiring multi-beam data. Over on the right, I love this newspaper actually in Greenlandic that shows a GIA map. In the lower right, an installation of tide gauge. And I will say, because this is just so cool, that this project started right just like a few months before the outbreak of the pandemic. And so almost immediately they had one meeting in Greenland altogether, and then almost immediately all travel was shut down. And since that time, our scientists have been shipping equipment like multi-beam data, multi-beam equipment, tide gauge equipment, everything to Greenland and collaborating over Zoom. And this project is being carried out by the locals in Greenland. And if you talk to the lead PIs at Lamont about this, they'll say that it's one of those silver linings of the pandemic that kind of almost forced the project to go in a different way that turned out to be a really great way. The second project I just want to mention is a project that is taking place. It's called Igavit-Sikukun, which means ice bridges. It's in the Northwest Alaskan community of Kootspi Sound, and it's led from the Lamont side by Chris Zappa over here on the farthest left of this figure, and he's a physical oceanography interested in what's going on with Arctic sea ice. And of all the things I could tell you about this project, I like this quote from Chris the best. The community made us aware of the importance of the river and ocean interaction and how the ice behaves around this area. The beginning and duration of the hunting season is determined when the sea ice and the landfast ice break up. After the exchange of knowledge with the community elders, we designed our experiment and observations around studying this interaction. The Elders Advisory Council played multiple roles as holders and enablers of new knowledge. So again, this is another group that would say their science has been greatly enriched by this approach. And I would imagine if I was talking to the Indigenous community here, that they would also say that this project has enriched and empowered them in their knowledge of their community as well. So I'll just leave you with that. And I just want to wrap up with what is my favorite cartoon And, you know, I just hope we do create the better world. I will say that I use this cartoon so much that about 2 years ago, I tracked down the artist and I wrote him and I said, do you mind if I use your cartoon in my talks? Some are recorded. And he connected me with his agent, and his agent sent me a contract, and I bought a license to use the cartoon. And a few weeks later, I got an autographed original of the cartoon in the mail from Joel Pett. And I think as you can see below, he writes to Maureen Raymo with admiration. I don't know if it's admiration because I might have been the only person that's ever bought a license to use a cartoon in a PowerPoint talk, or if it's because of my science. But either way, I think this is just a beautiful way to think about the future. And thank you for listening. And I'm happy to answer questions.
Thanks very much, Mo. That's really inspiring talk. So we have a couple of questions. We've got some a little bit more general and some a bit more detailed. And so we'll start with the general. So this is from Mary Gagan. And she asked, like, what, if anything, gives you hope for us making the right decisions to secure a safer climate future?
That's a great question. What gives me hope is the rate of change that I'm observing of the level of engagement of the business community, corporate leaders, foundations, and the change in government in the US. So that's what we all look at, rates of change, right?
Okay, so that's actually,
direction and rate is giving me optimism right now.
Right. So that leads actually really nicely in the second question, which is from Daniela Schmidt. So she says the geological record shows us that the rate of change is fundamentally important for the impact. So how can we slow the rate effectively?
Well, I mean, slowing the rate of change is everything about quickly lowering the level of atmospheric CO2, right? I mean, I don't, you all know it, I don't have to put it up. I have another figure of, you know, how we need to turn the curve and get the rate of sea level change, not only following the nationally defined contributions of the Paris Agreement, but even more negative. And in fact, you know, again, going back to that flask, I really, you know, if we don't get those emissions back under 400 in the next few decades, I think that the rate of change will have baked in a lot of sea level rise. I mean, that's the thing I'm worried most about, is baking in sea level rise, because even if we turn CO2 emissions down, there's still a lot of heat in the ocean, still upwelling under the margins of the ice sheets. Yeah, I don't know. It's worrisome, obviously.
Yes. So then we have another question from Matthew Status. He's asking, like, so you have advocated the need of co-production of knowledge, which is super important. And then he says, how vital is it for the climate science community to perform greater interdisciplinary collaborations within and outwith of the geosciences?
Yeah, that's really interesting. I mean, you know, not everybody's science is going to be amenable to the co-production of knowledge, right? I mean, it really is about how do you engage with communities that need to make decisions and need to adapt and need to mitigate, and how do they get and use the best information, and what's the best process and most effective process to make that happen, and make it less like, you know, the scientists parachuting in and saying, oh, we know what's best, do this. I mean, you know, nobody likes to be told what they need to do, obviously. So yeah, I don't know. I mean, this is a question that we're grappling with at Columbia University right now. We've just established a climate school, and Lamont is in the climate school. I see scientists around Lamont engaging with the business school to have studies about how sea level rise is changing real estate values and what it implies for bonds and this and that. I see another study of Radley Horton has set up a climate attribution database in the Sabin Center for Climate Change Law. So people that are thinking, okay, can I sue somebody because climate change caused this thing to happen that burned down my house? Well, you can go to this database and learn something about whether that event could be attributed and to what degree and with what certainty to climate change. So there's a lot of interdisciplinary, well, I should call it transdisciplinary work that's happening right now. And recently somebody said they wanted to do something that was like, I forget the word they used, but it was like no transdisciplinary, just busting out all the linkages between things. So, I mean, I think we're going to need to take a very holistic approach to climate change, and it's going to require new financing, new laws, new legal structures, new ways of doing business, all of it informed by the best science and the best projections of what's likely to happen and on what timescales. That's a long answer, sorry.
That's fine. It's a bit of an evolution for humankind.
Yeah.
Yes. So there's another question, and I'm not sure whether that's partly answered already, but I'll give it a go anyway. So this one is from Jennifer Scott. And she asked, does the sea level change variation analysis across the globe take into account aerostatic rebound and uplift? Did you look at that when, to see what's happening with melting in both Greenland and Antarctica for those studies?
Does she mean the 20th century sea level record?
Well, and projecting over it as well, I guess, yes. Well,
yeah.
I'm guessing yes.
Yeah, it is true, yes. I mean, for instance, GIA is ongoing, still changing sea level because of the melting of the ice sheets 10,000 years ago. The crust is still not at equilibrium. That change in sea level is factored into all the sea level projections, and sometimes it makes them a little bigger and sometimes it makes them a little smaller. There's dynamic ocean effects too. So yeah, this is why where you are is really matters. Where you are and what ice sheet is melting, it will make a huge difference, to almost to a meter, in what you can expect to unfold in the coming decades to century.
And then there's a question from Dan, and he says, because the biggest question and worry that you have throughout the side of your talk is like future sea level change. And he says, is there some other bits that you could expand on from the geological records that tells about sea level history? So from your own fieldwork and observations.
Yeah, well, I mean, I'm incredibly excited about this paper that Blake Dyer, who was my former postdoc, he's now a professor at the University of Victoria, is putting out, because we think we have the best Eemian sea level record that exists right now. It's based on a huge matrix of sites across the Bahamas. And it's low, right? And why is it low? It's low because we don't use the standard GIA model or one GIA model. We've looked at the complete spectrum of possible variations in mantle, upper and lower viscosity, in the size of the Laurentide ice sheet, the rate at which the ice sheets melt. And the thing is, there's a subset of GIA models that fit the gradients in sea level that are observed in the field across the Bahamian archipelago. This is spanning hundreds of kilometers, right? So if you have these observations and you have a GIA model that with the assumptions you put into the GIA model would predict, a gradient in the opposite direction, and clearly those assumptions in the model are wrong because we didn't map the gradients in the field wrong. That's how much confidence I have in our mapping skills, which is very, very high. So I would say probably the size you assumed for the Laurentide ice sheet is wrong. And in fact, if you assume the stage 6 ice sheet was much smaller in North America and larger in Fennoscandia, you have a whole suite of GIA model assumptions that fit the observations. And then you say, okay, now let's correct the data with those models, with those assumptions for GIA, and you get a much smaller, lower 1 to 4 meter sea level rise in the Eemian. Now, there's another reason that's really interesting, and this is the hairy edge of research right now. Is that because less ice melted during the Eemian? Or remember I told you why the Eemian was warmer? It was because of precession. So early in the Eemian, precession was stronger over Greenland, and later in the Eemian, precession, summer insolation, was stronger over Antarctica. So it might be that Greenland was melting early in the Eemian, while Antarctica was expanding and vice versa late in the Eemian, and just ended up so that the total sea level rise was, the mean of the two. And Bette, I was really curious to see your talk, because it seemed like something was alluding to that in what you were talking about too. So was it, what is the interaction between the ice sheets during the Eemian? Are they in phase? Are they out of phase? Are they going up and down together? Are they following local insulation? These are really interesting questions.
Yes. So how do you think we can answer that from paleo data perspective?
Well, the Bahamas is an incredibly unique place. If we had like 5 more Bahamas carbonate environments that beautifully record sea level and are biogenic carbonate factories, so that sediment is always deposited right to sea level, we would be able to do that easily. Unfortunately, the Bahamas are a pretty unusual place, but we are pivoting to the Mediterranean, which is on the peripheral bulge of the Finniscandian ice sheet, and there's ways to do it. So
okay,
there'll be more data, more field work, better models, better assumptions.
Thanks. So another question that's kind of a little bit outside of the talk. So you've recently worked extensively in the mid-Pliocene. And I was just wondering, are there any important lessons that we can learn from that time to take to the future of, what might be happening?
Well, I mean, the entire east coast of the United States, up to 50 kilometers inland was underwater. So that's a little disconcerting. So yeah, I mean, this is where 350.org actually had its origins, in a paper we wrote about the Pliocene back in the knots, where we said, okay, the Pliocene sea level was probably at least 12 to 15 meters higher, and PCO2 was more than 350, and that was the origin of that. Well, clearly we don't want to go there, and so 350.org was put in place to try to keep PCO2 under 350 to maintain a livable, sustainable planet. And again, this just goes back to this idea that we need to very rapidly decarbonize, turn the Titanic, the CO2 curve into the atmosphere, the rising emissions, turn that over, both by changing how we power our planet and also through active research in carbon dioxide removal techniques.
Thank you very much. I don't have any further questions. I don't know whether Dan Lunt would say some final words.
Oh, okay. Well, thank you. Well, huge thanks to Mo for such a wonderful finish to the day. That was a really nice summary of the state of our understanding of the relationship between geology and climate science. That was really, really spot on. And thanks very much, for engaging with all the questions. And a huge thanks also to all our other speakers today, and everyone who's engaged with it, either posed questions or responded to questions. Huge thanks to everyone. So just to remind people, we have the we're only halfway through. In fact, there's still, we've still got a lot more fun tomorrow. So we'll be starting at the same time tomorrow at 2:15 p.m. UK time, with a sort of an introduction, but the first actual presentation to kick us off tomorrow will be Danny Schmidt at 2:30 UK time. And the key thing to remember tomorrow is we've got a number of great talks from invited speakers and our early career researchers. But then after that, we also have these 1-minute sort of pre-recorded presentations from anyone who's submitted an abstract. So we'll hear some interesting ideas at that point. And then, crucially, we'll have an opportunity to discuss those posters and those people's ideas in the poster breakouts. And I think that could be a really nice opportunity to have some interesting discussions. So really look forward to that, as well as obviously looking forward to the talks tomorrow. So again, one last time, thanks very much to all the speakers, and thanks very much to the real organisers of this, who are the Joel Stock, and in particular Alicia Newton, and her team who've put this all together and enabled it to happen. So thanks to them. Okay, and we'll see you tomorrow. Okay, bye.